Zero.
Hi, Puneet.
Hello, sir.
Is
Hi,
it
sir.
clear?
Yes, sir. Bilkul.
Okay.
Everything is good. So, Shiva sir, everyone is here.
Good.
So,
Okay.
so Prerna is here, and Priti Ranjan sir is also here.
Good morning, sir. And good morning, everyone.
Good morning, sir.
Yes.
How are you?
So finally, all of us are at the same platform. So first of all, thanks a lot, sir. So I know like it was a very short notice for both of you, and both of you have just took some time. I know shoes are like it's all very busy for you. So, but
No issues at all. Yeah. My pleasure.
I'm very grateful. So right now, Shivu sir, we are also live on YouTube. Okay, and we started that particular part, and uh, Prerna is going to uh, take care of the things like okay, how to the schedule and everything.
Sure.
Okay, and looks like she is just facing some problem. She's right now. Yeah. So, Shivu sir, I'm going to make you co-host so that you can share your screen. So once
Sure.
Prerna is going to introduce all of us, then after that, I will just make you co-host.
Sure.
Okay. So let this is the internet word, and it looks like at the last moment things happen. Like Prerna was, yeah. Okay. So, Shivu sir, what we have discussed that from the video point of view, the first 15 minute, maybe we four will be on a video, and after that we will just switch off our video, and
Yes.
whosoever is a speaker, they can it's their choice if they want to they want to switch on their video. Okay, and it's my request to everyone also, like all the participant, if they can stop their video, because that's going to like create a yes. So and again, so I don't know, like other participants, like other attendees, maybe they are not in a way like okay, they want to show their picture to the YouTube live. So just make sure, like if you have not dressed properly, then don't switch on your video, because we are live on a YouTube also. Okay, so that's all from my side, Prerna. Now
Yes.
up to you. I think we are on time. Yes, even 5 minutes late. Yeah,
All
please,
right.
Prerna.
Okay. Thank you so much, Puneet. So, good morning, all of you, and a warm welcome to everyone in this first ever Expert Talk session and initiative by VLSI Expert. This is Prerna Bajpai, Administration Head of VLSI Expert. Want to thank you all for joining us today. And a special thanks to our honorable guest speakers to take time out for gracing our platform. Before we begin our session, we want to share with you all our vision and objective behind initiating the series of Expert Talk sessions. I'm just going to take a couple of minutes, it won't take too long. As you might know, VLSI Expert has been in the VLSI industry for almost a decade and contributing towards building an outstanding community of industry grade experts and professionals. Our goal is to build an enablement platform for aspirants to become ready to conquer technological challenges in the VLSI industry. And one of our core values of VLSI Expert is giving back to the community. We have always catered to a belief of serving people with advanced knowledge and awareness around the VLSI domain. So at this point, I'd like to recall a very well-known Sanskrit shloka. Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parabrahma, Tasmai Shri Guruve Nama. Everyone must have heard this shlok. It emphasizes on the essence of mentorship, the importance of having a mentor in our life. A mentor can be a confidant who instills confidence, a teacher or a professor, parents whom you look up to, a corporate leader, a social figure. We must understand that the mentors have a major role to play in our lives. These mentors, or should I say gurus, have struggled, gone through ups and downs, faced adversities, and made unrelenting efforts to reach to a point where they have the ability, charisma to inspire us. So the question is, how can we get inspired as much? How can we leverage their knowledge? The answer is through expert talk sessions. And through these sessions, we are making our sincere efforts to bring the experts on one platform where they can share their stories, anecdotes, experiences with us. And if these sessions can help in choosing a right career, shaping up the whole persona, and transform the life, our purpose is served. Um, I'd like to ask Puneet, since this has been his dream project, has been his idea, I'd like to ask Puneet to add to this.
Thank you, Prerna. So as such, I don't have much to add on here, at least in the expert talk. But yes, it is a dream project, and we just started today. So it's like right now we are just a baby, it's a baby thing, and I'm very thankful to Shivu sir and the Preeti Ranjan sir. Like the first ever talk, I would say, the initiative which we took it just to build a platform where every month people can come and they can just address uh, students, the professionals, and the job seekers and everyone. I'm really thankful to both of you, sir. And I know like both of you are the keynote speaker and everywhere. So for me, it's also like an it's a honor. Like you guys are just this particular platform. You become like an keynote speaker. So that with this, like Prerna, you already covered this thing. Like, okay, what is the vision and everything? For me, I just want to create a ecosystem, and through this expert talk is basically I just want to give something back to the community. And
Yes.
I have seen in the last couple of months a lot of people, lot of industry people, they are also trying to do this thing in one way or other
Mhm.
way. So what I'm just trying to do it, just creating a platform where they can come and they can associate with us. And through this particular platform, they can also address technical, non-technical, motivational, anything. So they can do
Mhm.
that particular part. So that's all from my side. And I hope the way we have planned the whatever the vision, I would say, like the dream I have, maybe if everyone will support, it will be, it's going to be like in a very rocking thing. Okay, so over to you, Prerna.
All right. Puneet, so do you want me to go through the informational pointers, the guidelines?
Yes, so I think
Okay,
you can just add few guidelines and then maybe we can just start the session formally.
perfect.
Okay.
So a few guidelines, informational pointers. If you have any questions, feel free to post those questions on the chat window. We'll make sure to address them either post session or offline. As you already know, that event is being live streamed and recorded for online, offline viewing on YouTube. And if you want to share the link with the ones who might not have, I mean, who haven't registered or still like to attend, um, I mean, they can go ahead and access this session. And the participants, the third one is the participants will be muted during the talk. So, and also it is a kind request to please keep the videos off during the whole webinar. And in case of, that's a very important one, in case of any unnecessary disturbance or interruption during the talk, that user will be removed from the session. Now let's begin with our first expert. what better way to kickstart this initiative than listening to our first panelist, an extraordinary technologist, an industry leader, a renowned philanthropist, a well-known social figure. Dr. Shivananda Koteshwar, also known as Shivu, is an IIM alumnus, has a doctorate in management education. He's currently a design group digital implementation site leader, R&D head at Synopsys Incorporated. Shiva is a mentor of change, Atal Innovation Mission, Niti Aayog, Government of India, SIG member, Electronic Sector Skills Council of India, and IIT Skill Development Working Group member. He's extremely active in mentoring startups, catering to edtech and learning space. He's a co-founder investor in Your Philanthropy Story, Asmat Guru Educational Services, Krida Lok, and Toolkit for Life. He's the founder trustee of Pelaku Trust, focusing on rural education, skill development, experimental learning. Shivu is not only a corporate leader, but also a dedicated and passionate teacher who works with K-12 schools, UG and PG and UG, PG and MBA colleges to bridge the gap between academia and industry. He's an adjunct professor in Dayanand Sagar University and an executive program partner in Orinco Design Preparatory College. So this was a brief summary. I had to snip a bit. The whole session would not have been enough to capture all your achievements and accolades. So without further ado, let me hand over to you, sir.
Thank you. Thank you, Prerna.
Thank you, sir.
Thanks, Puneet. Can you enable the screen share, please? So good morning, everyone, and welcome to the session. So my topic today is to talk about the advancement of chipsets. I know we have a good mix of students and professionals. So I'll try to start with the basics, but try to have some information for people who've been working in the industry for a couple of years. So with that, I'll be switching off my video because I don't want to hog my bandwidth. If there are any questions, feel free to send it out in the chat messages. I will ask Prerna to keep pinging me and asking me the questions. So you don't have to wait for the end of the sessions. You can ask me the questions if you have anything while I'm presenting the slides. Okay, so these are my coordinates. If any of my students want to connect, please use this LinkedIn profile. If professionals, I have already put it in the chat window. You can use that link to connect with me. All my slides will be hosted on the slide. And of course, this session is being recorded, so you will get the slides and the video of the session. But if you want the slides also, it will be uploaded on the slide share, so you can view the slides over there. So with that, let me start. So let me start with the basics so that it puts some context here. We all have studied CPU in our engineering or MTech programs, and CPU is nothing but a microprocessor which receives input data from the software. It doesn't matter what kind of interfaces we have, and finally outputs the processed information to various units of a computing system. So this is the definition we have learned in our college. What are the basic segments of processor? You all know, we have registers, control unit, and we have ALU. This is a very simple representation of the processor. Now, in some of the textbooks, they use a terminology called as general purpose processor, primarily because there are different types of microprocessors which has come. So it can be an embedded processor, it can be a DSP, it can be a media processor. So there are many, many different processors which has come after the invention of the CPU. So let's look at the different types of processors so that it puts things to context. So what has shifted right now? 20 years back or 25 years back, we were talking about system on a board, where the entire system was actually put on a PCB board. Today, what we are talking about is a system on a chip, which means the entire functionality of what the board used to do is primarily being done with a 3 mm by 3 mm kind of a chip, which means the industry is trying to push technology as much as possible, and the technology is pushing the possibilities and limits of physics also today. Right, and we all know the nodes we are working with right now. I started my career with 1.4 micron technologies. And today we are talking about 3 nanometer kind of technologies, right? So we have moved from from 2 microns or 1.4 microns to 0.8, 0.5, 0.35, 0.25, 0.18, 90 nanometers, 65 nanometers, 28 nanometers, 14, 10, 7, 5, and now we are talking about 3. So every 1.5 years or 2 years, the industry has moved from one technology node to the other technology node. And there is a reason for this. It's because of you and me. We are pushing the boundaries of what we need from a chip. And the functionality is being expanded. We want lesser and lesser power from the chip. We want to make sure we pack as much as possible in a chip. We want to make sure it's cheaper and cheaper as we go along. So all these different parameters, right, is pushing the chip design in a very nice way. So how did it all start? It all started in 1971 when Intel released the first microprocessor. And, believe it or not, it had 2,300 transistors. And it operated at 92,600 operations per second. And the next big innovation was Motorola 68000, which was released in 1979, which was a high performance microprocessor, which was selected by Apple. So that was a big thing for the market at that time. And of course, we all know Intel Pentium in 1993 changed the game for everybody else. So that was a 3.1 million transistors, which worked at 60 hertz. So that was a big change for all of us. And the first completely home brewed AMD processor was introduced in 1996. So Intel, Motorola, AMD, Sun Microsystems were the pioneers in the chip design industry. Now, the photo here, some of you might have seen, this is the first computer in 1946. And what is fantastic to see is it ran at 10 kilohertz. It consumed 140 kilowatts. It costed around $2 million and used 18,000 vacuum tubes, which is equivalent to around 18,000 transistors today. Took up 15,000 square feet of space, and it weighed 30 tons. This is how we started our journey. And today we are talking about SoCs, which is going to fit on your fingertips, right? So what pushed it? It is constant ask mark work on 4 things: performance, power, area, schedule, and finally cost. So we call it as PPAS, and then the 5th one is the cost. So these are the 5 different vectors or the demands from the industry or the market, which has pushed chip designers to move from what we see on this photo to what we have today on our fingertips or inside the products what we use. So that's the journey we have embarked, right? So what has happened in the last 10 years? Intel Atom was the first processor, right, which was targeted for a very different specification at that time. It was primarily targeted for tablet. It had a different curve after that. AMD APU, AMD Ryzen, and Intel Core i9. Right? These are the big changes which happened in the market. Intel Atom was a single core microprocessor for low cost notebooks. That was why it was intended. But again, things changed after they released that product. AMD APU 2011 was the first mobile-centric processor which had an accelerated processing unit. AMD started a different vertical at that time, which pretty much every chip industry has a product right now in that market segment. And the first Core i9 processor for laptops was released in 2018, and multiple versions were unlocked here, giving the users an option to overclock them for aggressive performance. So basically, the Intel gave an option to the users to control the performance of the chip. So this was the first time which happened. And 2017 is when AMD Ryzen was introduced. It was at 4.2 billion transistors, and it clocked 4.4 gigahertz. This is what has happened in the last couple of years. So this is a journey where we started in 1950 with 1 transistors, and we're talking about 8 billion transistors right now, right? And as I told you earlier, we started our journey with 10 microns in 1971, and we are talking about 3 nanometers or 2 nanometers in 2021, right? This is the journey of what we have embarked. And again, you can't discount the innovations which has happened. the Apollo guidance computer ran actually at only 2.048 megahertz, which took the first man on the surface of the moon back in 1969. So yes, this looks very small today, but this served the purpose at that time right now. And if you look at the power of the smartphone you have in your pocket right now, it must be 1,000 or 10,000 times the performance of what was there 10 years back. What is driving the market? Moore's law. All of us have heard about it. So basically, every 18 months, the number of transistors on a particular device is doubling. And this is Gordon Moore was a co-founder of Intel. He mentioned this in one of his presentation very, very early, and that was his observation. And we've been following. The market has been following it as a law. It is not engraved on a stone, but it is something which we pretty much have followed. And there are quite a lot of examples where we can map the DSP chips, we can map the GPU chips, we can map the microprocessors. We all see a fantastic alignment on the Moore's law. So that's kind of one driving force we have. And so what is GPU? Um, Earlier, we didn't have a separate graphical processing unit, right? A couple of years back, because there was not many GUI intensive work. When use of graphical user interface or GUI became a standard for operating systems, because earlier, I don't think you even know about it, but we used to have something called as a DOS system, which was a text-based system. We didn't have a GUI for the operating system. Once the operating system had a GUI attached to it, the number of graphic elements used across the interface increased a lot. So it required a different kind of a processor, which would render images more quickly and will process it better. So that's when the GPU was designed. And why GPU? GPU is designed for data parallelism, and that is one of the very basic characteristics of a the GUI. So that's the reason why we looked at a GPU processor. So we had CPU, then we started using GPU also into the system. Then came the DSP, right? So DSP was again early in the cycle itself. So we started using DSP, GPU, and CPU. And DSP primarily means digital signal processing, which is nothing but any signal processing that is done on a digital signal or information signal. That's exactly the definition of a DSP. And DSP processors suits perfectly fine for a high performance, repetitive, numerical intensive task. And there are few tasks which is very numerical intensive where DSP processors can do a better job on that. So DSP are just one class of CPU. But let's try to look at what are the different types of use in a microcontroller so that you understand and appreciate architectures of each one of these blocks. So you have CPUs, you have GPUs, and the third one I introduced was DSPs, right? And the fourth one, what we've been hearing, is NPU, which is a neural processing unit. What does a neural processing unit do? It primarily specializes in acceleration of ML algorithms, machine learning algorithms. It is also called as neural processor. It is 10,000 times faster than GPUs. And we have seen multiple examples, right, from Google, whether it's a TPU or from NNP or Myrad and IQ from Intel, NVIDIA layer from NVIDIA, and AWS InfraShare from Amazon. So there are multiple NPUs which is being designed right now for a specific application. So today, if you open up the box, you will used to see CPUs like what you have in your textbooks, but today we have CPUs, we have GPUs, we have DSPs, we have NPUs.
Okay, looks like we just lost, sir. I think he will come back just in a couple of minutes. Sure, sir. So you have to reshare your screen.
Sorry for that. So I think you heard me talk about NPUs. So can you hear me now?
Yes, sir.
Okay. So today, if you open up a chip, what you see is a combination of CPUs, GPUs, DSPs, and NPUs, and then all the other blocks which is required for a smartphone, for example, right? We have connectivity IPs, we have multimedias, we have sensors, we have ISPs, we have the displays, and we have the navigation system. So no longer is one processor, we have multiple processors. So what happens is there is a special controller which we put. Depending on the type of application, depending on the type of demands the user is making, it will send it to the right blocks for the processing. And whichever processor is right for that kind of an application, that processor is used. That's exactly what a controller does today, right? So that's where we are right now. And if you look at the smartphones today, earlier we used to talk about CPU, DSP, and today we have a host of different components like NPUs or AI accelerated chip, brain-inspired computing, neuromorphic computing, bionic chips, software-defined networking. Multiple different blocks have already added in to the smartphones because smartphone SoC is one of the most complicated SoCs to design and architect today. So yesterday, right, we saw this news, TSMC 2 nanometer SoC breakthrough mass production in 2023. And we are talking about 5 nanometer right now. And TSMC announced 2 nanometer just yesterday, right? That's something where the market is going. And every time people keep asking, is there, will it end at 10 nanometer? Or will it end at 14 nanometer? Will it end at 18 nanometer? And here is TSMC, who proudly mentioned yesterday that we will be ready for 2 nanometer. And for people who don't know, the first 5 nanometer from TSMC was a Qualcomm chip, which is a Snapdragon 875 SoC, which is primarily for a mobile phone. So that's the first SoC which has TSMC has taped out through Qualcomm has taped out and manufactured to TSMC, and this is where we are. Right? This is the technology enhancements we are talking about right now. So why are we doing all these things? What is the 4 staple food for these chips? One is data. The amount of data, right, which the microprocessor or the controller is having today is enormous, and mainly because of the IoT, right? And we used to talk about gigabytes and terabytes, and today we are talking about brontobytes, which is 10 to the power of 27. That's the kind of data. Now, when we talk about data, it has 4 V's, right? So there's a McKinsey report says. So it is the volume of data, which is the scale of data, which is a variety of data, which means you have different sources, which is creating different types of data. And then you have velocity of data, which means the speed at which the data is coming. Depending on the devices, the speed matters. And finally, the veracity of the data, which is the uncertainty. Depends on. So the system has to handle all the 4 V's. It needs to know how to handle volume. It needs to know how to handle variety. It needs to handle velocity and veracity. So when you look at all these things, you need a fantastic processor to manage these things, right? So that's one of the things which drives the entire advancements in the chips right now. So when you talk about data, as you all know, it is categorized into 3 things. One is all the applications around data management itself. And then all the different things we do for data analytics, and finally, all the things we do for deep insight. So these are the 3 different types of categories of work we do with the data. And depending on which category we are talking about, the size increases. So if you're talking about data management, we're talking about terabytes. But if you're talking about deep insights, we're talking about zettabytes. Right? That's the biggest challenge we have. So the first is data. And of course, analytics, we all know, we started with the information, and today we are talking about decision and action. So the journey was in descriptive analysis. We moved to predictive analysis. Today we are talking about prescriptive analysis. Tomorrow we'll be talking about preemptive analytics. So from being reactive, we are trying to be prescriptive right now. So that's a journey the data analytics have taken. The second one is machine learning, and we all know, right? So we have the big data here. Then you have the machine learning with the deep learning is one of the machine learning types we do. And you have the data mining and the data science on the left side. So the intersection of all things, right? With the data science and data mining, what are we teaching the machine? With that, how the AI is being developed. So this is where the second source of information and processing requirement which is coming. Third one is IoT. IoT stands for Internet of Things. It's basically anytime connection, any place connection, anything connection, right? So this is the third one which is driving. How big is the IoT market right now? Now, these are old reports. Things have changed right now, but to put things in context, it still works, right? So if you're looking at 7.6 billion world population, we are talking about almost 6.58 devices connected per person. So we're talking about 50 billion or more devices which will be talking to each other. What is driving this? It is primarily miniaturization, cost effectiveness, and planning of the smart cities. So digital and smart cities is one of the major things which is driving the market. So in some reports, it talks about 24 billion. Some reports, it talks about 50 billion. But we are at the range of around 40 to 70 billion devices for sure. And it's a 1.5 trillion market, which we are trying to address, and which is growing at a very, very good rate of 25% CAGR right now. And again, different technologies are enabling IoTs. It can be the sensors, it can be the bandwidth, it can be the processors, smartphones, multiple things are driving IoT segments right now. And the last one, which I wanted to talk about, is the AR VR. We all know, I mean, AR is something which will definitely pick up more than VR, according to me. And we have already started seeing edtech companies, for example, rolling out products in the AR segment right now. So AR is one of the big platform which is going to drive the processing market. So for people who might be new to this, AR is you bring the digital world to the real world. VR is you go to the digital world. So that's a big difference between AR and VR. So which means in a VR world, you need to wear a specs and you need to sit in one place. You can't be mobile. But in AR, you can be mobile, right? Because you're bringing the digital world to you. So that's the reason why AR market might be bigger than the VR market. This is a good example of AR, which was being experimented in metro stations in Delhi, actually. This photo is not from metro station in Delhi, but this is a virtual wall where the person actually can use a smartphone and do the shopping without having to see the physical asset. Right? This is just a virtual wall, and these are photos actually. Using the QR code, the person is able to shop. This is an example of AR, and this is what will demand more and more technology from the chip design market. Let's skip this. So what's the application of AI? Everything, right? Whether it's autonomous system, whether it's machine learning, whether it's neural networks, whether it's chatbots, whether it's virtual companions, thought control gaming, every sector you can think of, AI is getting in right now. So people, including chip design, right? So we already have, for example, in Synopsys, we already have integrated ML and AI in our verification suites. We have already announced integration of ML in our digital platform recently. There is a very good insertion of AI in the lifecycle management of the chips. So we will see more and more AI ML application in the SoC design also. And when we talk about deep learning, we are talking about both, depends on which company you work for or which applications you're looking for. Most of us might be looking at a edge kind of a application similar to your security cameras, or your smartphones or apps. It can be a server trading engines also, like the Amazon Echo, for example. Both the markets are demanding very, very high processing and memory requirements right now in the chip design. Some of the applications here, you have seen, I don't know how many of you have seen your photos which you upload on your Facebook. It puts this tags, right? And you'll be surprised to see the kind of tags it's putting. I don't know if you can read this, but one lady with a child has posted the photo, and the engine actually has put a lot of data, right? It's put one person, it's in the ocean, it's shoes, it's child, it's sky, it's outdoor, it's water. So these are the tags it's putting. And why do you think it's important for the user? It's mainly for marketing, right? So if you look at the second one, where the mom is feeding the child and she has taken a photo and uploaded on Instagram or Facebook, the AI engine, what it has done is it has actually scanned all the appliances she is using behind, right? And the photo actually reveals much more than what the mother wanted to reveal. The user right now knows the kind of products she's using, so they can start looking at targeted marketing for this person, right? So that's the kind of information you are actually uploading when you do a simple photo. And it's the same thing is true with the voice also, right? So technology requires faster computing and better computing. And very good products which was released last year, Google Pixel Buds, which basically translates real time any language to any language you want, and Sony glasses, which basically you can wear it and you can read the subtitles in any language you want. And of course, the movie needs to have those different subtitles. It cannot be viewed in the regularly when you see it, but when you wear the glasses, you'll be able to see the subtitles in the language you want. So these are some good applications and products which has come. So what is needed, right? Designing is a key component of innovation. In India, we are fantastic with development. We call ourselves R&D, but how much of R do we do, right? Most of us actually are doing only the development part of it. So I have started an initiative in Synopsys called Bringing Back R and R&D. Many forums I'm talking to right now, I just talk about this research part of it, because we have forgotten research, unfortunately. And research means people think it's in university. People think in corporate world we don't do research, and that's the biggest problem we have right now. So how do we bring back the R and R&D teams? That's one of the initiatives which I'm driving in Synopsys. I think you all who's working in your organizations really need to look at this part of it, and at least dedicate your 10-15% of your time on research if you're in the R&D team. Always watch the technology trends and track the growth markets. Today, the growth markets might be different because of the COVID reasons, but overall, the growth market right now is healthcare, automotive, wearables, and education. These are the 4 growth markets you have. The demand will come from there. And as chip designers, we are here to cater to the demands of the market, because it's a consumer-led market. So it's very, very important for you to track the growth markets and look at what might be the requirements of tomorrow, so that you can spend your time in these. I will not, the slides will be there, but I'll just give you these 3 markets which we talked about. Healthcare market, for example, is almost just the analytic markets is around $24 billion. And global health will be increasing from 9.21 trillion to almost 24 trillion by 2040. And we are talking about healthcare market, which is worth $158 billion by 2022. Just the treatment of diabetes will be exceeding $500 billion 20 years from now. And a lot of reports in the US, 1 in 3 might develop diabetes. So the numbers which the market will demand from us is so huge that so much of innovation is required to take care of this kind of a demand. Second, automotive, right? If I double click on a car today, this is the kind of electronics the cars have, right? It's got all kinds of electronics inside the car. This is just a subset of what the today's cars have. All these things require microcontrollers, require sensors, requires the electronics to manage these things. And earlier we used to talk about moving parts, and today we talk about how many lines of codes the modern automotive have. And this is the data which I found in one of the presentations. It has 50 electronic control units and 20 networks and 10,000 network signals, right? That's the kind of electronics you have inside a car. And if you look at the electronics, it's categorized to 4 segments. One is on automation, one is on security, one is on connectivity, and one is on electrification. So these are the 4 different segments you have within the automotive segment right now. The third one is wearable. So when you talk about wearables, it can be categorized in 3 major segments. One is in the medical field, one is in the wellness field, and the third one in the sport and fitness field. Usually there can be a single wearable which can do all 3, or we can have a specific wearable for different things. And depending on the consumer, if I'm interested in managing the vital signs, for example, if I want to monitor the vital signs, then I might use a medical wearable. If I'm focused on wellness, then of course I will look at the wellness wearable, and fitness freak. And there are different kinds of wearables which is out there in the market. So this is another segment which is driving the semiconductors market right now. And as I told you earlier, do track the technology trends. It's very, very important to look at how the technology is moving ahead. So we are at the bottom of this curve right now. We're talking about robotics, we're talking about blockchain, we're talking about nanotechnology, and smart what's happening around you, right? The climate is changing, global inequality is coming. What are the different environmental aspects which is going to hit us, right? Aging population, for example, urbanization, for example, technological unemployment, for example. These are different things which is happening around us. This is what is going to drive the market to innovate. And these are different technology roadmap which we are talking about, right? The future scenarios is what we should be focusing on and try to see what can we do. And the path for tomorrow is around ambient experience, is around exponential intelligence, is about quantum computing. So these are the three areas. Again, I don't want to get into the details. It itself is a one-hour presentation in terms of what different technologies we have. But in general, right, this is where the industry is moving. This is where the market is moving. This is where the user is moving. So it's very, very important for us as designers, as a solution provider, to track these technology trends and come out with solutions which might help the customer in this particular application. This is another chart just summarizing the different technology trends in the 2 years, in the next 2 years, and in the 3 to 5 years. These are the different, you might have heard some of these things in different topics or webinars, but this is where the market is going. This is where what is happening around us. So please keep a track of these things. And it's very, very important that we understand. I'm not saying you'll be an expert in all of those things, but at least you should know what's happening around you. Very, very important for you if you are focusing on research. Right? And this is 30 technologies in the next decade. Same thing summarized in a picture. So I thought I'll just put it here. People who are interested, listen to Ray Kurzweil. He is a fantastic speaker, fantastic innovator. He has done multiple things, but one of the presentation he's done in TED is called Get Ready for Hybrid Thinking. It's kind of a brain in the cloud kind of a concept. It's fantastic. It's something which is going to hit us very soon. Most probably in my lifetime only I'll see this. And the second one is from Geraldine Hamilton. She talks about body parts on a chip. And these two presentations are real. I mean, this is an old presentation. It's not a new presentation, but these are some of my good TED presentations which I've heard earlier. I encourage you to take a look at these two presentations. And when we talk about opportunities always lies not in the vertical, right? The verticals can be categorized in multiple ways. So let's say we're talking about home or transport or health, buildings or cities. Yes, there are verticals in each of these verticals, but the opportunity is there in the intersection of these verticals. For example, if you look at home and health, the opportunity lies in the intersection of home and health. The opportunity lies in the intersection of transport and building. Opportunity lies in the intersection of building and home. So this is what you as young engineers should be focusing on. Yes, you need to have a depth in a particular vertical. At the same time, look at adjacent technologies, look at adjacent markets, look at adjacent opportunities, where a combination of your skills in that vertical and an opportunity in another vertical, you might be able to come out with some compound applications. Let me give you some examples, right? In San Francisco, 20 to 30% of traffic congestion was happening because of people hunting for parking spot, right? They were going in circles. Most of the traffic congestion was happening because of this. Now, this is the data from transportation. What can you do? All you had to do was put a sensor in the parking lot and feed it to the driver and let him know which parking spots are available in the city, right? So it's a combination. It's an intersection of transportation and smart cities. This is one example where a compound application can be created, which will help answer the problem statement you have. Second one, we all know about this. 40 million adults age 65 and over will be living alone in US, Canada, and Europe, which means they need help, and they need help when they really need it. And this combined with healthcare. How can you alert the medical services when the person needs help? And all you have to do is think of a sensor, think of multiple devices which can be connected in the house, make your home a smart home, and address the healthcare problem. Right? This is another example of compound application. The third one is about smart buildings and mobility. Energy used by commercial and industrial buildings in the US creates 50% of natural emissions of greenhouse gases. So what can you do? It's very simple, right? As you leave the house, for example, if your car is connected to the building, you can switch off all the electronic and electrical devices. As you're approaching near the garage, we can switch on the AC at that particular time. So the smart building and mobility connected together to come out with some compound applications. So always think of intersection of multiple verticals. That's where the opportunity lies. And this is my last slide. I always say, right, whatever is worth doing well. Some of you students might be, you have things what you love, but there are jobs which pays really well, but you're good at few things. The intersection of these three things is what we look for. If you just end up in doing what you love and what pays well, it's just a dream, right? Because you're not good at it. So eventually the market will catch up, the corporate will catch up and you'll be fired from the job. If you end up in something doing what you love and you're really good at it, but you don't get paid, you're very, very happy, but you don't make much money. If that's a choice, is perfectly fine, but you need to know about that, right? The third one is you're good at something and it really pays well. You're really rich, but you're very bored. Many corporate people are in this segment right now. And most of you have heard about this word ikigai. So ikigai puts the circle there, which is what the world needs. So whenever you have an intersection of what you love, what you're good at, what pays you for that, and if the world needs that solution, that's the intersection of these four circles is called as ikigai. And I really appreciate Puneet and multiple people like Puneet who's doing something like this, because it helps people get direction. It helps people identify their strengths. It helps people. I don't know how many of you seen his blogs. I always encourage a lot of students to go and read his blogs. It's taken so much time to put some of this fantastic information and training modules online. This is what can make you good, right? So that's very, very important. So you need to understand, you need to train yourself, you need to identify your passion, you need to land in the right job, and you need to look at solutions which helps the society. So this is intersection of these four circles is called as ikigai. So with that, I will stop my presentation. I have few minutes, so let me take a few questions. So let me look at chat window. If there is any questions over there, I will answer. If anybody else has any question, you can please let me know.
Thank you, Shiva sir. Sir, I did post one question which was asked by Abhishek Rao on your chat box privately.
Why don't I see the chat? Let me unshare the slide so it'll be easier for me to.
I can read the question, sir, if you like.
Please.
All right. So the question is, how does the upcoming depression affect the rate of growth of chipsets sales and manufacturing?
So there is a very nice article in on the net. Just take a look at it. We have not seen a dip, surprisingly, right? Yes, there are few markets who have taken a small dip, but there are other segments which has taken a huge uptick right now. So every time there is this is not a depression for that matter. This is just a dip which the market has seen. People have become a little bit cautious. That's it, right? Nothing else has changed. People are going ahead with the 5G deployment. There is no change in that part of it. You might have seen multiple announcements. In fact, Reliance announced next year India will get 5G. So 5G deployment has not slowed down because of COVID. Hiring has not slowed down because of COVID. Synopsys has hired 140 people, if I remember the number correctly, in the last 3 months, doing virtual interviews, virtual onboarding, right? I know the same thing is true with Cadence, same thing is true with MediaTek, same thing is true with Intel, same thing is true with Qualcomm, right? All the chip design companies and EDA companies actually have hired people during this pandemic. So there is no slowdown in hiring. Yes, people are becoming more cautious, no doubt about that. They want to get the right set of people, and it becomes a little bit difficult for companies to hire also because you don't have an opportunity to meet the candidate. So we depend a lot on the virtual platforms. So if you're a person who's not able to put your best foot forward on a virtual platform, sometimes it's you might be on the wrong side of the fence, but so it's very, very important for you to practice and see how to manage virtual interviews, for example. Right? It's very important skill set to have today, but it's not reduced. So
thank you, sir.
somebody has a specific question for me. How's the growth of AE in Synopsys? I've been shortlisted on online exams and interview. Even whether I'm in Synopsys or not, I would strongly recommend Synopsys because I worked there for 11 years earlier, and I'm back in Synopsys in the last 2 years. I know many of the AEs who have grown from a fresh grad to what they are today. I mean, one of the most sought after engineers in semiconductors are the Synopsys AEs. So if you are someone who wants to learn, who wants to be challenged all the time, who wants to be kicked with the technology advancements, then definitely join. If you're someone who wants to chill, not work much, please don't join.
Hello.
Thank you, sir.
Yeah, so the other question I saw was, what are the key research areas in the field of VLSI in the upcoming areas? Right now, it is a lot of focus is given on machine learning, ML application on flow development, ML application on memory utilization or memory reduction, ML applications on place and route technologies right now. So there is a lot of machine learning research happening within the company and in the universities, and also the research sponsored research which we're doing with the IIT Kharagpur and IIT Mumbai. So a lot of work is happening on the ML side and on the test side, design for test. So these are the two areas I see a good opportunity for you guys. There's another question which says, can you give me some tips on virtual interviews? There are multiple platforms actually for virtual interviews. It's not, when I say virtual interviews, I don't mean just one-to-one speaking, which we can do it in Zoom or WhatsApp calls. I'm not talking about that. I'm talking about the ability to take online tests, for example. There are coding tests which is being offered online. So, you need to be aware of those things. You need to know how to manage multiple devices and manage the tests online. If you have a digital slate, for example, that really helps when you're doing, when you're writing tests. So it's important to invest on devices which might be required for you to manage some of these things.
All right. Thank you, sir. Thank you for your valuable time and informative session.
Thank you very much.
So Prerna, I have one question.
Sure.
So sir, maybe a lot of people know you very well, uh, like what you have achieved and what you are doing right now. But I think there are a couple of people, there are a couple of students, they need some uh, motivational thing. Like if anyone just want to be you after a couple of years, maybe after 10 years or 15 years, then what exactly they should do? So that's I think one of the thing, like, okay, about your journey. Like I know, like you're uh, uh, doing things, you're following your passion, but still, if something you just want to tell to these even the people who are in the industry, like what they should do, maybe that's going to help them a lot.
Two things, right? One, whichever job you've landed in, put your 100% there, right? Be the best in what you do. And there is no substitute for hard work. You just have to work hard to achieve whatever you want to achieve, right? There's no definition for success. It's up to you how you define your success. It can be position, it can be money, it can be learning you do. It's up to you. But whatever line you chose, please make sure you put your 100% into it, right? Don't while your time away. It's very difficult to get back time. Okay. Second is, never stop investing on yourself. There are beautiful courses which is available out there, both technical and management. Don't wait for somebody to come and tell you that you need to upgrade yourself in ABCD, right? It can be soft skills. Till date, I attend, if there is a soft skill training in Synopsys, I go and attend because there is always something to learn. There is absolutely nobody in this industry will say, I've learned it all. There's nothing more to do, right? Nobody is going to say that. So there is always opportunities for you to learn. And today, thanks to technology, we have beautiful courses on Coursera, for example. You can attend MIT courses, you can do Stanford courses. I'm not saying you need a certificate. You don't have to pay for the certificate. It's not about flashing certificates on your LinkedIn, but if you get an opportunity to do some courses, please do it. And a lot of people ask me, how do you manage time? How do you? And I thought I should just show you this. This is something which I found on the net, and I think this is the best slide I can summarize. How do you manage time, right? And it's up to you how you manage your time. All of us have 24 hours. We all have to sleep. We all have to work, but you get that extra 9 hours to do whatever else you want to do. So if you're able to manage your time effectively, I think you'll win. So it's up to you how you manage your time and what is your priority.
Puneet, did we lose him?
Looks like no. So he's there, but maybe.
I just finished talking.
Okay, okay. So yes, sir. I think that last slide that was the good one. Like even the way you have distributed your time, like 3 hours, 8 hours, and yeah,
Yeah,
three and three, the 9 hours. That the way
yeah,
you have distributed. I think that's a fantastic thing, because I was about to ask you like how you're managing your time, because you're doing a multiple things. It's not like you're doing a single thing. You're doing a multiple things. And I always ask. I always just tell to uh, everyone, like in the age of 40, in the age of 45, in the age of 50, I have seen people are doing a lot of things. They're managing their time. And the age of a 20, 25, like students, they are just saying that they don't have time to study and they don't have time to do the courses. I think all of you guys should think about once again like how you're managing your time, like the way the Shivu sir just mentioned that particular part. I think that is done. Yeah, so I'm good, Prerna.
All right. Okay. Thank you so much, Puneet. Thank you, Shiva sir.
Thanks a
All
lot,
right,
sir.
let's move on to our next honorable speaker, um, Dr. Preeti Ranjan Panda. Good morning again, sir. Yeah, let me just give a brief introduction as we're running out of time. Um, Dr. Panda is an exceptional scholar, embedded systems wizard, highly respected in the realm of academia. Professor Panda, an IIT Madras alumnus, has got MS and PhD degrees in information and computer science from the University of California. He's currently the head of School of Information Technology and a professor in the Department of Computer Science and Engineering at IIT Delhi. He has previously worked at Texas Instruments, Bangalore, and the Advanced Technology Group at Synopsys Incorporated, Mountain View, and has been a visiting scholar at Stanford University. His research interests include embedded systems and computer architecture, CAD, VLSI, memory architectures and optimizations, hardware, software, co-design, and low-power design. He's a recipient of an IBM Faculty Award and the IESA Techno Mentor Award. His research works have received several honors. Professor Panda currently serves as the editor-in-chief of IEEE Embedded Systems Letters Journal. Dr. Panda, if you are all set to take it away, I would like to hand over to you.
Sir, I gave you a permission, co-host. I think you can share your screen now. Great. So we can see your screen.
Okay, shall I start?
Yes, sir.
Okay, thank you. It is a pleasure to speak on this platform. Thank you all for joining. It is actually a privilege to follow the previous speaker and the talk. It actually set the agenda in a very nice way in the form of a survey of the technologies that we are currently working with, and a survey of the markets that we are headed towards and that this industry is going to be addressing. The flavor of my presentation will be slightly different. This is, after all, coming from academia, and we will talk about some collaboration between academia and industry as we speak about some of the research issues, but we will try to build up towards some research challenges that come up in a very natural way in this industry. Obviously, the industry is very large and lots of problems coming up. A couple of directions were already alluded to by the previous speaker. I will talk about some of the background that I am familiar with. So this is still, again, not everything in the VLSI industry, but a certain thread in the design part of it. But that's also an active area. There's lots of research happening. There is lots of research happening in India and in IIT Delhi particularly. I will try to touch upon some of the interesting things, what kind of challenges are involved there. Hopefully, people will find something that is different, something that's new. Particular emphasis that I'll try to lay on is some of the interdisciplinary challenges that come up. Sometimes as we go through a degree program in electronics or VLSI or computer science and so on, we are exposed to a bunch of courses through which we get some view of what this area is, where is it headed towards. But often some of the very interesting give and take that happens between our field and some adjacent fields, we might or might not get exposed to. That depends on the curriculum. But we will try to consciously identify some of these areas that lie at the intersection, particularly between electronics and VLSI on one side and computer science on the other. It should be very clear, the way the previous talk went, that there is a lot of give and take already. After all, VLSI is addressing the demands that are posed by the computing infrastructure in some way, so that hardware is developed and so on. So, of course, the motivation should be clear, but yet some of the connects might not be very obvious. And through this talk and through some examples that I'll be showing of interesting new research challenges and classical topics that evolve into some of these interesting new areas. Hopefully, one of the primary things that you will take away from this talk is how does VLSI design and electronics interact in a technical sense, particularly with interact in general with a broader community and broader set of areas, of course, but particularly what are these connects? Where are these connects technically between VLSI design on one side and computer science concepts on the other? That's an area that we play in, that intersection in this interdisciplinary area between electronics and computer science. And hopefully I'll be able to share some of the excitement that's generated in the area. So let me turn the video off if I can. Okay, so let me turn my video off, and then let's move on with the agenda. Okay, so the one that I would like to focus on is the point about raising abstraction levels as we perform VLSI design. And synthesis is that mechanism through which we go to higher and higher levels of abstraction. What does that mean? We will look at through an example. Yeah, this talk will be of the kind that we will try to build some things from ground up to the extent that we can. So I'll put up some explicit examples later on. But synthesis is that process. Some of us, of course, through our college programs, we would have invoked some of these tools, synthesis tools, to generate circuits, to generate FPGA designs, emulations, and so on. So we might have used it. We might not have too much of a glimpse into how the synthesis work. Companies like Synopsys and Cadence and so on are the players in the market that have perfected these products commercially for decades now. It continues to evolve. How it evolves, what is the direction that it evolves in, those things we will try to take a look at. I'll try to introduce in a very elementary way what kind of things happen there and what are the challenges that we are moving towards. But abstraction levels have been rising in order to accommodate complexity. What that means we'll soon get to, but that's the first part. We motivate synthesis, raising essentially the level of abstraction. That should lead us towards the design of complex SOCs, and which in a natural way lead to problems like hardware, software co-design. It's not merely that we are worrying about designing of the hardware and the circuit and the layout and so on. That's one part, but every complex chip involves several other things. It involves software. Where does the software come from? It is because there is embedded processor inside our SOCs. SOCs consist of some custom blocks that are custom designed, but of course there are other blocks that are microprocessors, like it was already motivated in the previous talk. So we'll take a look at these, and in each of these spaces we'll try to identify some conceptual problems that could be formulated by a researcher to take a look at it, that if there are good solutions for that are proposed early on, then one can try and follow through with a commercial plan. Early on, these things would be in a research mode, but sooner or later, if the ideas seem promising, then some kind of a handoff would happen into the industry and into the commercial space. This process is not necessarily simple. It's not necessarily easy. What we are talking about synthesis is a technology here that that companies have been using for more than 25 years, more than 30 years now. It's somewhere in the late 1980s that commercial adoption happened of synthesis. So this is a classical and sort of an accepted design methodology. Yet this didn't come about overnight. The early academic efforts at the automatic generation of electronic circuits date back to the 1960s, early 1960s. So in fact, as something like a 20-year, 25-year transition period, which is what a typical technology might take from the time that it is first investigated in an academic research environment, in which you simplify some of the things perhaps, but go deep into optimization, try to explore all of the options, to all the way into a commercial product. The process is actually, it's very interesting, but it's also very painstaking, and that a time from research to product might actually easily be decades, and one ought to be prepared for that. If we are serious about the technology, that newer technologies that we are proposing, we ought to have that kind of patience for so that kind of gestation period, which could easily be 10 years, 5 years, 10 years, 20 years, and so on. So yeah, we'll talk a little bit about that. And in the context of the new complex SOCs, we can look at several new technologies that interact in various ways. One of the things that I'll try to give an insight for is that memory technology continues to evolve in some very interesting ways. And when memory evolves, the technology changes, everybody else has to be aware. All other layers of the stack, as it were, on the hardware stack, on the software stack, everybody is influenced by such evolution in technology. So yeah, let's take a look at then in what ways are we involved? What are new interesting problems that come up if memory is stacked into a 3D system? We'll try to look at some of those insights. And well, nowadays no talk is complete without mention of AI and machine learning. So it is an obligation to talk about what is the interaction. Actually, Synopsys tools that we heard about, and that there is an integration of ML and so on in the EDA flow is itself evidence about the seriousness with which these algorithms, these strategies are being taken all over the software industry and the hardware industry. But we'll take a look at what some of this interaction means. Where are those opportunities? So that's how I have structured the talk. And following that, I'll be happy to engage in any discussion regarding any of the topic. And of course, I will also give some idea of the sort of things that we are doing here in our lab. There's a lot of very interesting research going on in the area that is an intersection between hardware and architecture and several other disciplines. I'll briefly talk about it. So that's how the talk is structured. Above everything else, if there's one thing that I would like particularly students in the audience to take away from this presentation is that the process of VLSI design, even though if you just look at those words, it might seem as though it's all about circuits and layout and so on. That's one level of abstraction. We'll talk about different levels of abstraction, but the entire process of chip design is a very exciting interdisciplinary field involving many things of electronics, concepts from electronics, concepts from computer science. All of that might not be obvious as we navigate a course structure in an engineering curriculum, but in fact, there is a very intricate dependence. In fact, the design automation industry, where companies like Cadence and Synopsys play, are actually representatives of this very exciting interdisciplinary field. On one hand, you are dealing with electronics, the analysis of electronics, synthesis, generation of electronics, and on the other hand, there is an analysis that's to be performed, which is automated, right? So the moment there is automation there is algorithm, there is data structure, there is everything else which harks back to typical things that are maybe typically classified computer science, but in fact, there is a very strong interrelation between them. That's one theme that we will get back to and remind ourselves of through these examples that I'll be talking about. Okay, so let's look at VLSI synthesis. This is something that that many of us in our courses might have come across, particularly if you wrote some hardware description language in Verilog or VSDL or something like that, and you submitted it to a tool which is an FPGA design tool, and there was a synthesis tool that took that HDL specification, which is more like a looks like a software programming language description of our circuit, and translated it all the way down to gates and later on to physical design and so on. That's what essentially is synthesis. And what happened through that process is the abstraction levels went from higher to lower. That's what we go through. And if I can abstract out this process itself is actually very intricate, that a synthesis tool goes through, or an EDA flow goes through. So we will pick up just some milestones along the way, some checkposts, and talk about what's happening and what's involved in going from some higher level of abstraction to a lower level. What you are starting from might be a behavioral level there, where there is an algorithm level specification. This is a functionality that we are trying to design. We are not going into too much detail of the timing, what is going to happen when, clock cycles, modules. We might not even know what our target architecture is, and this could well be just a software like a C or a C++ or a system C kind of a description. Maybe ultimately it's going to go down into a hardware path, but as of now, there's actually there's hardly anything there that is hardware specific in that sense. So we start off with that. Then when we decide that these are blocks that are going to be taken down into a hardware path, there is the need to talk about a register transfer level. That is what is called an RTL model. Here, some transition has happened from a pure functional description. Now we are talking about clock cycle boundaries. So we have introduced clocks in our design. It might still be higher level design. It might still be an SDL, but some idea of a finite state machine is defined. What states our system is going to go through, what are the concurrent activities, all of these things we might already have a picture of. So that's what I would call an RTL model. Going down further, so this is still only a high level description, and we would translate that down into what is called a gate level. So that net list of gates is something that might actually be something that's very common. What to do about it, how to optimize it further. That's why there is a loop out there at the gates, which is we start with gates, but we have some ideas, tools and algorithms would be there for optimizing a gate netlist for area, for timing, for power, and so on. We might stay here for some time. And once we are satisfied with this, we might go down further into the lower level of abstraction, which we are here calling layout. That might be a standard cell technology, some kind of gate array technology, and so on. This actually spans what you see here from left to right. A great change in the level of abstraction. It doesn't happen in one step. There are a number of steps that we go through here, but conceptually you could think of breaking up into these kind of steps. Each of these one can call as a kind of synthesis that takes us from a higher level and puts in more and more detail that are hardware specific. Introducing clock boundaries is one level of detail that takes us closer to hardware. Introducing gates is another level of detail. This is still conceptual, right? These are still diagrams with symbols and connectivities that are of a logical nature. So this doesn't capture much physical information. But later on, when you go into layout, that's where there is more geometry that is captured there. And it is in some ways much closer to what the die and the wafer ultimately look like. So these are all the synthesis steps. These are the going from the behavioral to RTL, we might call behavioral synthesis. RTL to gates, we may say RTL synthesis. Optimizing gates, we might put this under logic synthesis, and finally all the way down to layout. Maybe there is a layout synthesis, but we don't necessarily end there. There's a physical design is also a complicated flow in itself. There is timing analysis, there is extraction, many other things, but just to keep this talk more focused, I will talk about these kind of levels of abstraction. Our interest here in this talk is to investigate what are the challenges at higher, relatively higher levels of abstraction. So this is just preparing us for where we might be moving towards. But that's sort of an encapsulation of the different synthesis steps. It essentially, each of these steps takes us to a lower and lower level of abstraction. Okay, now let's zoom in into high-level synthesis. We do want to stay at a little higher level of abstraction for the purpose of this talk. So let's see what kind of problems do we address. How is it that an algorithm that is specified is ultimately translated into a netlist structure, which is where we would like to move towards, right? So so on the left here, we have an algorithm that we said earlier, there isn't any specification of timing or such. We just say y is equal to a plus b plus c. Okay, so that's kind of a functional specification, we can say. And when that's given to us, you can think of submitting such a functionality to a synthesis tool. And the synthesis tool somehow has to go through the process. Let's see what is the first process that we would go through. Let's capture this simple functionality a plus b plus c plus d in the form of a graphical design that you see on the left. So there is an addition operation doing a plus b. There is another addition operation doing c plus d. And finally, we add up the results. Not the only way to structure this, but anyway, this is one way to capture the functionality. The visual capture here is significant. This isn't merely um, a, a picture that enhances the presentation, but in fact, there is a deeper connection that we will soon get to. But for now, you could think of any SDL specification or programming language specification to be captured in some way in what is essentially a graph data structure. So this is where actually there is the first link you can see from first the specification itself. That specification looks very much like a programming language specification. Then it is internally captured in what could be a synthesis tool into a graphical data structure, graph-based data structure. That's the other connection with computer science, because these are things that come up in a data structure course that we might take. The representation should be intuitive. A, B, C, D are the inputs here. Y is the output, and those nodes that we see here in that graph, they represent our operations, and these edges that are there in the graph represent flow of data from operation to operation. Right? So that's our that's the capture of our functionality. But that's just the first part. The question then is, now we would like to introduce the idea of a clock. So far, there is no notion of a clock. Remember that behavioral design didn't have any idea of a clock. But we would like to insert some clocks here. How do we do that? Essentially, on the right, you see these dotted lines that essentially that capture for us the mapping of operations into clock cycles. We are saying that the first two should happen in the first clock cycle, the next one should happen in the second clock cycle. That seems like a simple change, but in fact is a key change that is necessary in the lowering of the abstraction. We have got closer to hardware, right? Early on, it seemed as though it was a more like a programming language description. You could do anything with it. You could submit it to a C compiler also. But for a synthesis, for submission to synthesis, this could be our first step in lowering the abstraction level, which is we put those dotted lines there. They represent what operation should happen in which clock cycle. That's what is called scheduling. Okay, why is the scheduling important? Now, with this partitioning of time into clock cycles, we could then infer a finite state machine corresponding to every clock cycle. There, every control step here, we say that in step one, we do these two operations. So that let me call my state one. In the second cycle, I do some other operation, let me call that S2. So in some ways, a finite state machine is inferred in a direct way from the schedule itself. I'm not obviously going into complications, but just conceptually describing what might happen. Okay, so that's one. There are some other interesting things. We are here trying to sort of give a high-level picture of what are the problems that go into a high-level synthesis process, where we start off with just a functional description, and finally our target is to come up with a circuit, right? So which are the steps that we would go through? Now let's see that we have a scheduled graph on the left. I have to make this another decision related to the resources that I have available with me. Those somehow I have to pick up from some kind of a resource library, and make this decision of which operation will be implemented by which resource. So that's a decision in which clock cycle. So essentially I'm saying that in the first clock cycle, the first operation, the first adder will be implemented by the color here indicates which resource. And the same color being used in the second operation there in the second clock cycle means that in the second clock cycle, since that resource becomes free, maybe it can be reused for that other operation. So what we are saying is that there is some sharing of that resource across these two operations across time. Since it would be free in the future, let us reuse it for something. So such decisions would have to be taken in what is called a resource binding step. That actually already takes us a little closer to a circuit and hardware, because actually implicitly, even as we talked about this, we made some decisions. We made some adder decisions, we made some multiplexer decisions, even though I didn't explicitly say that. For example, we decided that 2 adders will be used, one of each color. So these are the 2 adders you see on the right. We also decided that one of these adders is going to do one operation in one clock cycle and a different operation in the second clock cycle. That means that there is some multiplexers that would be needed perhaps at its inputs, so that we can implement that kind of resource sharing that we talked about. So in some natural way, we can now construct at least a skeleton of the data path that suddenly begins to look like a circuit. As of now, we were not talking about circuits. We were talking about just a conceptual capturing of a functionality and dividing that into clock cycles and so on. There was no notion of a circuit, but suddenly you see that if I decide the resources, if I decide the sharing of the resources, then at least part of the circuit is ready. This is not the entire circuit, but it's part of it. But this looks good. It looks promising in our journey towards ultimately a layout that we would like to generate. Okay, let's move on to one other component, which is maybe there is some storage that we might have in this design. It would be very rare to find a design in which there is no storage. You always have different kinds of storage, maybe registers, maybe memories, SRAMs and DRAMs and so on. You would have that. We will pick on this, pick up and expand upon this later on in this presentation. But yeah, actually implicitly, as we did scheduling, there are some decisions we took that implied storage. For example, there was this variable here that we saw there is an output from an adder. That result is produced, output is produced in one clock cycle. It is being used in the next clock cycle and also in the next clock cycle, right? What's produced in cycle 1 is used in cycle 2 and in cycle 3. So that means that I need a register to store that data, right? So that means that in fact there's a lot of things that we could infer, circuit related detail that we could infer from those decisions that we made earlier. So that's a register. For all these outputs that that we want to use in a different clock cycles, we might want to store them in some D-flip-flops registers. So I have one output there of C plus D F that's being used in the second clock cycle. So for that, I might need a register. That result of the adder in the second clock cycle is used in the third one. For that, I need a register. So yeah, you could think that if there's a variable that is persisting across a clock cycle boundary, then there is the need of a register. But that's not all. Actually, there are some very interesting problems that come up conceptually here. The thing that you can see from this simple example itself is that an output that we are calling F, that's produced in the first clock cycle, used in the second one, and the other one that's produced in the second one, used in the third one. Maybe I could share the space because what I produced early on, I didn't use later on. So that actually creates for us a very interesting register sharing problem. The problem is now when I made all these decisions, how do I minimize the number of registers? I should be able to implement that with the circuit, but I don't necessarily need one register with every for every variable. Maybe I can reuse a register to store different variables at different points in time. So that's my register allocation problem. Once I do that, then you can see that I have almost my full data path circuit. I have my adders, I have my multiplexers, I have my registers, I have my sharing decisions. So what goes into the muxes and what comes out of the mux, all of that is there. Actually, this is beginning to look much more like the kind of electronic circuit that we are more comfortable with as VLSI engineers, right? But what this sequence of steps pointed out is that you could well have started from a very high level description, and in fact all these decisions are steps in the synthesis process that led us to a data path circuit. You don't finish here. In fact, there are some other things that are necessary before we can declare victory here in terms of the electronics. One is, of course, that data path, what's there here in the dotted lines is that data path that we just constructed. But one other thing that comes here and interacts is that finite state machine that tells the data path what operation should be performed in which clock cycle, what whether that A should go into through the mux into the adder, or that other operation E should go into the adder. So there is some control that is necessary. These how do we implement that? There are the select inputs to the mux. Those need control signals, and those control signals have to be generated by the FSM. But remember that the FSM is also generated. We already have that FSM, at least a preliminary, the structure of that FSM is there. Some more details need to be filled in, but that's our design. FSM I am just leaving as a leaving here as a symbolic structure. I'm not, but then we already know, given a finite state machine diagram, how to translate that into circuit. Yeah. So this was the the set of synthesis steps. I thought it's good to outline these. While these are classical matters, these are established topics. Tools are already there in the market that perform such things, such automatic translation. These are topics that we don't necessarily study in an engineering curriculum. So I thought I could go through some of these steps just to give a flavor for what are the internal steps of a synthesis tool. It's one thing to just invoke a synthesis tool, but another to develop some deeper insight into what actually goes on there, so that if I need to improve the design in some way, if I'm not getting what I expected, I could get some pointers through this understanding of the synthesis process regarding where the interventions could lie. So yeah, the other point was to emphasize that there's actually a pretty deep computer science interaction with the VLSI synthesis flow. You see that the graphs are involved, so there is a data structure involvement. You see that what are these scheduling, binding, register allocation? These are algorithms, right? So algorithms need to be, we need to come up with, and even though the strategies might have seemed simple in these examples that we saw, in reality, it's actually not that simple. These are actually pretty complicated. Some of these things like scheduling, these are classical computer science problems that are difficult computationally. If there are 3 nodes in the graph, it is a trivial problem. But our node, we don't have 3 nodes. We are talking about hundreds of thousands of functional nodes in that way. So which actually pose pretty serious challenges to a synthesis tool in terms of how to compose a scheduling algorithm, binding, sharing of registers, and so on. It's a very fertile area where people are still working on, depending on what the technologies are, how to perform a good job of the synthesis. It's an old topic, and it's a topic in which commercial tools have been there for a long time. Nevertheless, while there is adoption here in the market, there is still a lot of scope for new things that are happening. There are other computer science concepts: database, object-oriented programming, compilers. What is the synthesis tool doing? Actually, there is a pretty strong overlap between the way a compiler works, let us say, takes a C program and generates instructions, and the way a VLSI synthesis tool might work. It's not obvious, but if you think about it, you see that they both are doing an efficient translation. The equivalent of C or C++ is our HDL. Equivalent of dates, you could think of as the instructions, right? Those instructions are those low-level things in a processor, and you could think of dates as the low-level, corresponding low-level thing. But there are some nice overlaps. It's not identical, but there is a lot of overlap. Of course, in addition to this, the computer architecture is all about hardware, and what we are designing in VLSI, there is an obvious relationship. So these are the things that I wanted to illustrate in some way. So you can think of what we talked about in terms of synthesis as sort of laying the groundwork and the foundation for design VLSI design automation tools that start with higher levels of abstraction and take us down the hardware part. But it would be an interesting view for us to climb up the ladder even further. So let's assume that synthesis works for us. Synthesis of custom hardware blocks works for us. We don't stop there, right? Modern SoCs have embedded CPUs. In Shivu's talk, we already saw that there are processors there are caches, there are GPUs. What you see here is an old NVIDIA SoC, but you have parts of it which are doing some image processing and video decoding. These are specific blocks for which we are designing custom hardware, right? Which you can call this as hardware accelerator or a synthesized block. But that's not all. There is memory on chip, there is some audio block, there are some USB blocks and so on. But that's not all. What you also see is that in addition to these custom hardware blocks, there is also some software component here, which is executed on CPUs and GPUs and all of those things. Those are also there on chip. Therefore, our SoC is actually a very intricate system from a high-level architecture point of view, for some of which we may design custom blocks, but the others, maybe we just get an ARM CPU or an Intel CPU and instantiate it in our design, and our real design is a lot more than that. That throws up interesting system level challenges. There is a hardware versus software. You have some functionality. Should you execute it on the embedded core? Should you execute it on the GPU? Should you design explicit hardware for it? These are actually very interesting system level design problems. Interestingly, it could be also captured conceptually using this graph structure, which we will not go into too much, but you can think of capturing your functionalities in terms of, let us say, these nodes on the graph. Again, we are coming back to this graph because it's such an important structure in the analysis of these systems. Here, maybe the nodes represent some kind of functionalities. Maybe video decoding is a functionality, no longer simple, but more complex functionality. And these edges, maybe they represent a flow of data or connections or something like that. And our high-level mathematical problem here could be that I want to divide that graph into two partitions. One partition on the left refers to all those functionalities for which we need custom hardware, and the one on the right refers to functionalities that will be done in software. And so there would be some kind of an automated process, a reasoning process that we can go through, provided, of course, that we model our system well in terms of what the node here means, what the edge here means, and we formulate some problems that we can then solve in an automated way. So yeah, this is the other connection of a system level design. We have grown above the synthesis. It is a full chip design, SoC design, but here too, I'm pointing out there is some interaction between computer science concepts and electronics. Right?
So with that, let's take a look at a couple of very interesting modern examples of technological directions and the ways they influence this high-level design and research in system level design. Some of these things, actually, these are problems that we are actually looking at, we're trying to address in our research groups. And I thought I'll put that up here because industry is moving into some of these very interesting directions, and there are interesting examples. This is what you're seeing here is a 3D structure. So there is benefit to stacking dies in the vertical direction because your bandwidth could be higher, they are more compact, and so on. So there are some very interesting, there are performance related reasons why you would like to do that. But each of these technologies has some issues. This actually has some thermal issues. As you go from the periphery towards the center, one interesting thing is that these memory ranks here, they become hotter and hotter. The channels become hotter. As you go from the bottom vertically upwards, they become cooler. So it's cooler just because there may be a heat sink at the top, but power dissipation at the bottom might not be so good. So there is a thermal gradient that you might see both vertically and horizontally. This is a physical effect, but there are some intricate ways in which we can pose this as a system design problem and come up with a solution. This is a physical effect. You can't do anything about it, but you could solve it in various ways, being aware of what's going on. It could be that, let's look at this high-level system in which we have processors as a DRAM, but what's interesting is there's a 3D DRAM that exhibits this very new thermal gradations that were earlier not there. Well, you could think of various solutions to these. You could think of maybe initially when you notice that temperature is going up in the central channels, maybe you could swap some data, right? Maybe you could do some dynamic voltage and frequency scaling to operate at a lower frequency. With that, maybe the activity goes down. If it doesn't work, maybe you can shut down certain channels. Not necessarily everything. If you shut down the whole thing, then of course the performance takes a hit. So you could shut down the channel partially, and a shutdown means what? There is active data there, so data has to be migrated out before you shut down. So you have a partially working system, but it's still working. It is better than not working at all. So you could go through some sequence of channels to be shut down, and maybe at the end you can throttle it where the system is actually not working at all. The 3D system is not working at all. There's some very interesting challenges here. And what should be the sequence of shutdown? Should you migrate or should you not migrate? This would have to be done based on a queuing model of the traffic and so on. You may have to predict where the temperature is going. So very intricate system level design problems come up from what is essentially just a physical observation that temperature is rising. But it's not random, it's not uniform. There are patterns there, and we could exploit such pattern in different ways. Let me introduce a couple of problems here just to illustrate the interaction between hardware and machine learning. Some of the examples we actually from the EDA perspective, the previous speaker already spoke that there are many of these EDA technologies where timing and some of the others where he already alluded to ML algorithms being used. What we are pointing out here is a complicated CPU system in which you have processor cores, you have some on-chip network, you have some shared cache, and you want to do runtime optimizations for performance, for energy, and so on. What do you want to do? Maybe there is some voltage scaling decisions that I want to take for all the cores. Maybe for the on-chip network, I can scale the voltage. Maybe I can partition the shared cache in some way. So there are many runtime problems that a system has to solve. And what we are pointing out here is maybe you could use, because it's a complicated solution, not easy to formulate in terms of a clean algorithm. a reinforcement learning or some of those variations could be used, where those agents could be monitoring. Agents for us in hardware could be that these are simple counters that are monitoring various events, and they're monitoring the components, and they take a coordinated action which is overall improving the total system throughput or energy or such things. But such problems actually the um, expose us to very interesting applications of modern algorithmic technologies like machine learning strategies. So that's where I thought I could conclude. I wanted to acknowledge the contribution of a lot of my PhD students and postdoc in our group. It's a large group with many of these problems. Some of the problems that I talked about, the students are working on it. We call this the group MARG, Memory and Architecture Research Group. And some of the kinds of problems that we are looking at are cache management of the kind that I mentioned, emerging memory technologies like 3D memory and non-volatile memory. So when that technology changes, what are the system level problems that it imposes and how to solve it efficiently, how to come up with hardware accelerators and machine learning. Shivu talked about the NPUs, how to design hardware blocks that do ML efficiently. Those are one, and design automation. So some of these are the ongoing research areas. These are areas that we've been collaborating over decades with companies like Intel and NXP, Cadence Semiconductor Research Corporation, which is a consortium of different semiconductor industry companies and so on. It's a very vibrant research ecosystem. There are lots of things that are happening. So that's where maybe I can just summarize. We talked about the higher levels of abstraction, and actually as we went through the talk, we went higher and higher in the level of abstraction. This is sort of key to scaling up to large systems in which you have billions of transistors. And one of the things that I wanted to emphasize was this is a very heavily interdisciplinary area. Like a good electronics background is necessary so that we understand the physical effects, but knowledge of computer science concepts um, will help in various ways because there are all kinds of applications of data structures, algorithms, compilers, operating system, machine learning, and so on. It's a very exciting time in which interdisciplinary stuff is happening at a very incredible level. So irrespective of whether our background, of course, as we go out of college, we don't have all these backgrounds, right? We would have a certain background, but it is good to keep our eyes and ears open with respect to picking up and absorbing knowledge from all these adjacent fields, because invariably they help us become overall a more complete design engineer or a system engineer. So let me stop here. You're welcome to check up further on the sort of projects that we look up that we've been interacting with and my contact information is. So maybe I can stop here, and if there are questions, I could take.
Yes, Dr. Panda, there are a couple of questions. Do you want me to read the question, sir?
Let me stop. So should I just stop the share so that we... okay, fine.
Okay. There is a question by Kumara Pujit. What kind of changes are required in computing architectures with the development of NVM technology, which are capable of in-memory computing? And how will this influence software design?
Yeah, this is a really interesting question. Actually, if you looked at the slide, while I didn't talk about non-volatile memory here, I did want to touch upon the emerging memory because it is so important. It's there everywhere. I talked about the 3D memory as one direction, but yes, NVM is the other one. And in fact, we are very interested at a research level. There are lots of very interesting problems that come up. But in fact, if you look at prototypes people are building, it's very clear that in-memory compute, so computation and memory technology is merging in some ways, a very hot area. Many people are looking at it from very different angles. And that's that's something that seems to be opening up a lot of very different avenues that have previously been touched upon, not necessarily explored too much. The problem is, in fact, it arises from the data movement that Dr. Koteshwar earlier had referred to. There's so much data that is being processed by these beasts here, computing beasts, that there is a very natural need to optimize the connection between the interaction between the computation part of it and the memory part of it. It could be that the memory is totally different, and you are just you don't touch the memory at all. These are the regular DRAMs, but in fact it never works that way. There is the need to integrate the memory technologies on chip in many different ways. Non-volatile memory could be outside, but non-volatile memory can also be inside, like a last level cache could be of a STD RAM or a PC RAM and so on. So yeah, the technology is evolving. This actually this exports some very non-trivial problems to the system designer wherever you are. You know, we don't just stop at the hardware design, right? There we go one level up higher, the operating system, the compiler, all the way up to the application. If for example, if part of our memory is going to be non-volatile, this means that if the application programmer knew, or the compiler had a visibility into a possibly hybrid structure of the memory, maybe part of it is SRAM, part of it is non-volatile memory, then intelligent decisions could be made by the programmer or the compiler or operating system, wherever we are in the overall stack. There is the need to make that decision. Should I keep my data in one kind of memory, or should I keep it in the other kind of memory? It's a sort of a very fundamental problem that comes up. If it is going to be compute in memory, then you can see that my compilation procedure from the top completely changes, right? Now I'm not just talking about simple instructions, but I'm talking about finding out extracting much bigger patterns and then farming it out into complex structures, which are these computing memory. So yes, there are very intricate system level problems that come up, affects everyone. These are very interesting problems that academia certainly has latched on to. Can't cover all of them here, but yeah, absolutely that new direction of research and development and ultimately productization is certainly acknowledged.
Thank you, Dr. Panda. There are a couple of more questions. Puneet, would you like me to go ahead and?
Yeah, you just ask a question. I
Okay.
think a lot of people have questions, so I think we should address few of them.
Okay.
Yeah, I
So
to take up maybe some. I'm aware of the time, so maybe I can go in that order that I see. Yeah, there's a few more. So one is saying, can we get the slides of the presentation? Yeah, absolutely. Maybe I'll offline get in touch with Puneet, and who can make it available. The video, of course, is available, but the slides I'll be happy to hand over. Let me go forward. Other than RTL coding, what are the important concepts needed to be learned by an undergraduate student to think of the job profile of a verification engineer? Yeah, this is an interesting thing. You know, there are these design tasks. The moment you get to the industry, you are exposed to all of these very different tasks, right? There is synthesis, there is specification, there is simulation, there is verification involves, there's a formal verification, testing and post-silicon validation and so on. Unfortunately, from our college, we don't necessarily get a good enough view into this entire gamut of digital design. But with the point of view of what are the backgrounds to pick up, it's always a good idea to pick up, in addition to the VLSI and the design and the coding in HDL. Of course, coding means you are verifying that, so some kind of a simulation, we better know how to do. So, but that's of course taken for granted. There is a synthesis. It's a good idea to use an FPGA platform to start with that RTL coding and then use the tools to generate synthesis so that we understand some of the limitations of the tools. It's also a good idea to think about it from the tools point of view. That's where the computer science concepts of some data structures and algorithms, I said, those are good things to pick up. It's not a bad idea to pick up some background of how these synthesis algorithms or these verification technologies work, because it's always good, even if you are looking at it from a designer's point of view. When you come up against limitations of the tool, it's always a good idea to have some insight into why those limitations are there and how you can get around those. So yeah, so let me go over to the next one. 3D memory is still in R&D or in production. What are the main benefits on 3D memory over 2D? So yes, this is in the pipeline. Two things. One, the main benefit first is you get higher bandwidth, right? Because of the 3D structure, the number of pins the number of parts of the memory that you can simultaneously access through those silicon vias. We didn't get to talk about too much about the technology itself, but anyway, per unit time, you can extract more data, more bytes from a 3D memory, so than 2D. So that's the main benefit. It's not all benefits. The performance wise, there is a benefit, but cost wise, because it's a new technology, costs are higher. The integration has more challenges. 2D memory is an old technology. So yeah, this transition is still being worked out. So we talked about thermal challenge, but cost is also another challenge. Second is 3D memory is still in R&D or in production. Okay, so it is not there in a regular on a desktop kind of a system, laptop kind of system. You might not see it, but in fact, it is there in production. HBM is that protocol, and some of the accelerators like NVIDIA's neural systems. So some of these ASICs, application-specific chips, they do use the SBM standards, and 3D memory is integrated overall into the system. So yes, it is in R&D. It is not merely in R&D in the companies, not nor just in the prototype mode. It is definitely in production. Well, I do want to respect the time. So if there are more, I can certainly, if questions that we cannot handle, I can certainly engage offline. One question was, is it okay to do MTech in VLSI, or we necessarily require industrial experience? In some of the things that I talked about are hopefully things that are covered in the MTech test. So certainly when we teach MTech programs here, we give students exposure to both the technology side and technology circuit processing, that side, and also some of the EDA. So courses are there pretty much. It is the option of the student often option and the initiative of the student to take up. Sometimes some of these things that I mentioned of an interdisciplinary nature, they are not insisted upon by the college, but still it is a good idea to even if nobody is asking you, you yourself be aware of what are these, where are the directions that, for example, design is going, and pick up the courses that we're talking about. Okay. Yeah.
Thank
So
you,
maybe
sir.
I should stop here because I am sure there are other things. Puneet's talk is also coming up, so perhaps I can stop here.
Thank you, sir. Thanks a lot, sir.
Thank you, Professor Panda, for your insightful session.
It's my pleasure. Thank you.
Thank you.
All right, now we move on to our third guest speaker.
Prerna,
He's not.
just 1 second. Okay, let me just mute everyone, and then maybe I will just unmute you. Yeah, Prerna. I think now, uh,
I'm good to go.
yeah, 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 sure.
Okay, thank you. So, Puneet, let me just give your brief introduction to all our attendees. Our third guest speaker is not a guest, but a man behind the whole and soul of this initiative, Mr. Puneet Mittal, an epitome of sheer hard work and dedication, who loves to do every work with intricate details. He's someone who plays and he displays a never say die attitude. A BITS Pilani alumnus, founder director of VLSI Expert, a VLSI passionate, and a great motivational speaker. He has been working for the last several years to bridge the gap between the industry and academia with the help of seminars, workshops, skill development programs, guest invitation based lectures. He's also an active member of advisory board in education sector from school level to university level in terms of designing curriculum, training faculties, infrastructure building, and advanced learning techniques using technology. He has trained hundreds of aspirants professionals in the field of static timing analysis and foundation of VLSI design across the globe using offline online medium. So let's welcome Mr. Puneet Mittal. Puneet, you can take it away.
Thank you, Prerna. So just give me 1 second. Let me just share my screen, and then definitely we can just talk about. Okay, great. Okay, so I'm good. I think every one of you can see my screen. Am I right? Okay, great. I think yes. I consider that as a yes. Great. So guys, uh, all of you know me. I don't know like how much you know about me, but yes, uh, few of you know me very well. And Prerna already mentioned this particular part. Like, okay, this is one of my dream project, and I just want to see like, okay, this is the first time. This is the first lecture. So what? Uh, uh, Everyone just asked me like, okay, Puneet, you have to speak. So you have to come up with some topics so that students or even for the industry people, they should get something from you. So the topic which I choose today is VLSI industry as a career option, a myth and the reality. So the reason I'm just talking, I have picked this particular topic. There are a lot of questions which students or even the professionals, they are asking me, they are pinging me on my LinkedIn account or my WhatsApp, because and those questions are coming from the different background. Like if someone is from a software industry, they want to jump into the VLSI industry. Maybe someone is a dropout, maybe someone is pass out, and when it comes to changing the profile, like one profile to another profile, how you can change your profile, how you can change it. So that's one of the question people usually ask. So what I just did, I just capture a few of the things here in terms of so that was a thought process, I would say. And on the basis of that particular thought process, I thought like, okay, this is the great platform. It's a live session also, it's a recorded one also. So why can't I just come up with my experience, whatever the experience I have. I'm just doing the mentoring from the last several years. So why can't I just capture those numbers, the facts which I usually explain to everyone half an hour, 1 hour. So why can't I just prepare a few of the slides, and then uh, just, just explain everywhere. So there are a couple of facts which I'm going to definitely uh, present here, like which is an undisclosed facts. So when I'm saying undisclosed facts, it's like you will not find people discussing about that particular thing. Not even it's written in any job description, job ID, like okay, uh, we are not going to allow these people, because if they will do it, then there are a lot of questions people can raise it. Like as a student, you can raise a lot of questions to the company, like, okay, why this type of thing. But I will give you a some numbers, some facts, and that will give you an idea. So that is on the basis of my experience. Again, there are a lot of industry people in this particular platform. There are a lot of from the academia side also. And I'm not sure, like maybe if I heard someone and if they feel like, okay, why Puneet is talking about all these things. But uh, I would say, like, okay, everyone, like an industry people in academia, even the attendee, that's a fact. And somehow, whether you agree or not, that's a something day in day out students are facing and the industry is doing. Maybe as a manager, as a director, maybe you don't appreciate, you're not going to appreciate those particular thing. But that's the thing the is happening in the industry. So I'm going to just give that particular part also. So as such, the agenda is like, first I'm going to discuss about three important things: pillar, killer, and a builder of our career. So what are those pillars? And we think like, okay, the from the killer point of view, like, okay, what are those things? So I'm going to discuss about that particular part. And it's not like only for the candidates, they are seeking for VLSI industry, or they are looking for the job. It's for them also, those are already in the industry. Then I'm going to discuss a couple of slides, like, okay, what is the future prediction? A lot of people have this question, like, okay, what is going to happen in the future of the VLSI industry? So I have one slide just to give you an idea, like, okay, what is the future of VLSI industry? uh, Shiv already discussed about that particular part in detail, but I will just give you one slide. Type of the companies, nature of the companies, most of you may know, but like I was saying, this is one of the awareness talk. So I'm just going to give you an idea, like, okay, this is the type of company and the nature of work. And then the last one is the myth and the reality. I am going to discuss three things. What is the fascinating data? Why everyone just wanted to enter into the VLSI industry? That's one thing. What is the reality? Like, okay, what actually is happening, which you can't see right now? Maybe you can see once you will enter into the VLSI industry. And like I have mentioned, like the disclosed thing, disclose undisclosed facts. Slides are just a very simple one, and maybe I will be able to finish on time. Then the last, you can ask a lot of questions. Okay, so that's like I will just try my best. Like, okay, we'll just finish it up within the next 25-30 minutes, and then you can ask questions. That then is going to be an open house. So the first thing is the pillar of our career. So what are the pillars of our career? Education, everyone know, like, okay, the education which we are getting in a college and an institute, that's a pillar. And it's not like so when I'm saying the college and the institute, in this I'm also including the brand name also. Like, okay, if you are from IIT tier 1, tier 2, tier 3, so that is very important. Like, okay, what type of education, from where you're getting that particular education. And when it comes to the second part of the education, the second part of the education is the skill set and the learning. So as a process of this particular education, what exactly we are learning, what skill set we are getting. So these are the two things which is a pillar of our career. But sometime I have seen it, people or the candidates or the students, they focus on the first part, like, okay, we need a tier 1 college, and we need a tier 2 college. Or if by anyhow, by the, like, if the parents, they just force them, they just enter into the tier 3 college. And but they don't understand the importance of the skill set and the learning. So even in my college days also, in my time also, even now also, it is very important what skill set and what learning you're getting from the college. So it's going to be a huge discussion. I Whenever I visit a particular college, I discuss a lot, like, okay, how skill set and the learning is important for everyone. irrespective of from where you are, in which particular institute, what brand name you have. So I would just say on this particular part, because the pillar of our career, there is a lot of resources in the internet. Like Shivu already mentioned this particular part very clearly, that learning is something which should not, which is like you have to create your own learning map. So it should not be like you just stop it after your 4 year graduation or the MTech and done. So learning is a continuous process, and the day you will stop learning, uh, I can say like, okay, is going to be a is going to be basically a uh, counter. So your reverse counter is going to start. So you should focus on that particular thing. Second pillar is the industry. What type of industry, in which industry we are entering, like VLSI industry, embedded industry, communication industry, or IT industry. That is very important. And within that particular industry, what type of profile we are talking about. So what type of work you're talking about. So I have a very beautiful slide, or I would say like I'm going to use it to one. I am going to introduce one terminology later on, and that particular terminology will help you to understand like what profile, why I'm talking about a profile, like why the profile is very important. But for you, remember, always remember, like, okay, if you're working in a particular profile and if you're thinking like, okay, you're done now, at least if I'm talking about in the VLSI field, because this talk is around the VLSI field. In the VLSI field, in a there are a lot of profiles. When I'm saying the lot of profiles, it's almost like if you will just go into the in a particular company, you will see there are almost like 10 or 20 profiles, and from across the different companies, the type of the companies, the nature of the work, there are the different profiles. So you have to see like, okay, what type of profile you are working, and the culture. The culture of a company is very important. Most of us, we don't understand like, okay, what is the meaning of the culture. So now the culture is uh, whether it's a supportive culture, we just help each other and just grow, and it's just like we just grow, and we don't care about like, okay, what is the growth of my employee. So as such, this is a big platform, but still I'm just sharing this thing. There are a lot of companies, uh, they don't care, and even if the from the company point of view they care, but in the team they don't care. So that's the one of the thing, like the culture of a company, culture of the group, that is more important. Now as a employee, as a candidate, it doesn't matter. Sometime maybe you can start blaming game. So that's the third portion. Like even if there are challenges on education and the industry, the third pillar is the attitude. What type of attitude we have, whether we have an attitude of the blaming or the bagging. Like if we are going to blame, then definitely we have to bag. So it's just like you can understand like, okay, if every time for your success, if you are going for your unsuccess thing, if you are not successful, for your failure, if you are going to blame someone else, then definitely you have to beg in front of a people for your success also. So that's the attitude. uh, that's a pillar of I would say your career growth. And the second thing is the working and the winning. So if you just work hard, if you just focus on your learning, working, then definitely you will win the things. So it doesn't matter what type of culture of your group, what type of profile you have, what from which college you are, what type of skill set you have. So obviously if you're working and the learning, that means you're upskilling yourself. So in the entry, if you have if you don't have any major skilling, if you don't have the expertise, but if you are learning continuously, then there will be a time, then you will be a expert in a particular field. So that's a pillar of our career. Next is a killer. This is a very important slide, I would say. Like, okay, what is the killer of our career? The first one is a salary. So it's not our salary, it's a someone else's salary. That is a something is a killer of our career. So the moment you will start comparing your salary with the other salary, irrespective of checking it, like, okay, how that particular person achieve that particular salary, then I'm telling you, like, okay, you will uh, always try to achieve, you will just always try to catch that particular part, and you will stop learning, and you will just see like, okay, other person is getting a lot of money. So this money is a something, or the package is something, the salary is something, at least in the VLSI industry, frankly speaking, if you are if you have skills, if you have the expertise, it will come automatically. But if you don't have all those things, then no, nothing is going to happen. So that's a first one of the killer. The second thing is the self confidence. Maybe you may be thinking like, how can a self confidence kill you? So it's basically, it's a self confidence. The moment it become a overconfidence, you will never come to know when it become a overconfidence. So at least for the student point of view, I never ever heard this particular one sentence like, okay, sir, I'm not capable of doing this particular part. I never ever. If you will ask any student, can you do this? They will say yes. Can you can you just study for 10 hours? Yes. What do you think? Are you going to do the hard work? Yes. That those are the things which everyone is saying. Everyone, because they have a confidence. Okay, I can do it. And why they have this particular confidence? Because of the third factor, which is a small circle. So they are comparing themselves with the family members, with the friends, with their college and the seniors, the college seniors, and they think like, okay, we are able to achieve certain things. Because it's not like we can achieve it, it's just like the other person, he or she, they are not able to achieve it. I can do it because I know more than those people. So that's our confidence, and that confidence is basically the overconfidence, because we don't know what is outside. We don't know there are people better than us, and that's a something is a big killer. So the moment you convert this self confidence into like, okay, I have to learn. There may be something outside which I don't know. There may be people outside, they don't, they know better than me. If you have this particular thing and then work hard, then definitely it will be your builder. But right now, uh, most of the people, like more than 70% of people, or the students, or even the industry professional, whenever I interacted, they have this problem, like, okay, they have this particular thing, I can do everything and I know everything. That's the biggest challenge. Third, small circle, I already mentioned, like, okay, always we compare ourselves with our four boundaries. We always think like, okay, these are the people and I have to just be in the next level compared to this. I have to be the better than these people. So I always tell everyone, it's not about the better, it's about the best. You have to be the best. Now when I'm saying the best, then you can understand everyone, like, okay, so it's not like in compared to those 5, 10, 20 people, I'm the best. No, you're better than them, but you're not the best. So you have to just think in that particular way. And the last one, which is very important, and that is the unawareness, half knowledge. We just think like, okay, diesel is a VLSI, that's all. So that's a notion people have. That's a thing, we think like, okay, we know everything. So but actually we are unaware. And awareness is something which, if you think like, okay, if you just go with the one article, two article, and then you are done, it's not like that. It's a continuous process. So if you have if you just want to know something, basically you have to read it. You have to read it. So like I said, always you should have a single thing, like, okay, I need to learn it, I need to understand what else is going on in the industry and outside world, and that just discuss with the people, attend the conferences and all other things. So that's something is known as the awareness. So unawareness is a big killer of our career. We are trying a lot just to give this awareness thing, and this platform is one of the reason we are trying this particular part. And let's see like, okay, how we can contribute there. Now let's talk about what is a builder, how we can just go to the next level and build our career. First thing is very important, that is a mentor. If you have a good mentor, then he can change your life. Now, I can understand it's very difficult to get a mentor, but I think from today's session, you can see, like including me, now you can see there are three people. Shivu openly mentioned this thing. This is my LinkedIn profile. A student can connect with me on this particular profile. If they have any question, they can ask on the LinkedIn. He mentioned that particular part. So he is a big mentor. So now when you're getting an opportunity, sometimes we just miss it. So that's the something you have to make sure, like you don't miss. If someone is coming and if you're finding someone as a mentor, just connect with them. If you will just get a 5 minute 10 minute then a 1 month also, that is more than enough. So either you should be self motivated or you definitely need a mentor in your life. So that's a very important. That mentor may be your teacher, that mentor may be your parents, maybe one of your senior also. Sometime I have seen like okay, your junior also, like junior in terms of like in terms of the age, he or she can be your mentor. Mentor in the sense, at least obviously they are more mature than you maybe. So it's just like there is no age of a particular mentor. Don't think in that particular way, but the point is you should seek and you should just search for the mentor thing. And once you find the mentor, just stick to that particular guy, because they can build your career also. Second thing is, again and again I'm talking about the skill set. Everyone is talking about the same thing. Learning is a continuous process, and at least in a VLSI, I'm telling you, like okay, the day you stop learning, your things are done. Again, I'm going to give you the example of a Shivu. If you just go back and just see his education, then you will come to know. Even now, he achieved a lot of things. Even after that, still he is doing. He is connected with the education. So like he did the MBA, PhD, then the lot of certifications he is doing. So that's something is a skill set. If you will ask me, for me, I'm just running a whole company, I'm just doing a business and everything, but this is a part. If I'm not able to upskill myself, if I'm not able to get something out of a particular talk, if from a particular um, course or a particular portion, like okay, if any particular book, so it looks to me like okay, I'm missing something. So I just need to upskill. I every not the every day, because I cannot do that particular part, but yes, every week or every month I have to upskill in any area. And the last thing is, the builder is the interest and then the satisfaction. So if you have an interest in a VLSI, then only opt for VLSI. If you don't have any interest, if you're just going for the sake of money, I'm telling you guys, after a few years, you will say like, okay, you're not satisfied, you're not happy, and if you're not happy, you will not be able to perform well. So interest and the satisfaction, these two things are very important. If you're if you have an interest and if you are going to do that particular part, things are going to change. And then it doesn't matter whether you have a support system, whether you know people, whether uh, is basically uh, I would say the tough path, or it's like you don't have any mentor, you don't have any skills. But the point is, if you have an interest, you can just do anything. And you can build your future also, you can build anything. So that's very important when it comes to the from the career point of view. Now let's talk about the next portion, like okay, what is the future and predictions. So I will just go very fast, because both the speakers they have discussed about the future of VLSI industry. Now it's basically, you can see this thing. So this is a old one. So if I'm talking about what is the data from 2015, this is a something prediction till 2030. And now you can see this is a part of a transistors, the physical property of the transistor, how it is going to change and all other things. So we are in a 2020, this is a 2030. There are companies, there are institutes, there are institutions, they are doing a research and they are predicting and they are planning for the next 10 year, 20 years. So this is a 2015 2016 data, and on the basis of that they plan for the next 15 years. So this is a something you have to just check on, like, okay, what is the future of your industry. This IoT we was talking about till 2025, this is the prediction. And uh, and this is the data, old data, 2015 data. Somehow I would say, just say like, okay, I didn't get time just to come up with the new data, but this is the data just last year data when I just downloaded from one of these source. So you can also just check this particular part. Then there is a another thing which a lot of people usually ask about the Moore's law, and they just try to understand like, okay, what is going to happen. Like Shivu was saying, it's a 2 nanometer. Still, we are talking about the CMOS, and the CMOS FinFET. We are talking about the 2 nanometer. There are a lot of things. There is a one more technology on which from the last couple of years, not the couple of, I will say almost like from the last 1 decade, more than that, uh, people are doing experiments, they are doing the research, and that is related to the spintronic. Basically, we were just talking about the electronics. Now there is the next era is going to come around the spintronic. When it is going to come, I don't know, because from the last 20 years, I know like, okay, uh, the researchers, they're talking about this particular part. But it's the same thing. If you are in a VLSI industry now, it doesn't matter. So VLSI doesn't mean it's just an electron. It doesn't mean just the current and the voltages. VLSI is a very large integrated circuit. The way any particular process, any particular technology, if we will use it and we will just say, like, okay, this is, I'm just working in that particular part. It's a VLSI semiconductor. So all these things in a semiconductor, what is the electron holes? Then we usually talk about the spinning of the electrons. So we can go till any dimensions, I would say. So that's the next era is going to be like an spintronic. So I always say like, okay, at least I can give the guarantee right now. I can give the guarantee like till the time I'm alive, at least VLSI industry is not going to die. So don't worry. At least you don't worry. Your future is secure. You're going to work in a VLSI slash semiconductor industry. It doesn't matter whether it's going to be the electronics or spintronic, but yes, you are going to work in a VLSI industry. Now the question come like, okay, all these things are good, future is good, what type of companies are there? So I just give you in the 2 slides, I will just give you an idea about what different type of industries are there. Usually we divide VLSI industry from the type of companies as the three: design companies, fabrication based companies, EDA companies like Synopsys, Cadence, Mentor. These are the EDA companies. Fabrication like TSMC, Global Foundry, even the Samsung is also a part of fabrication based company. Design company like, Intel, Broadcom, and then ST Microelectronics, and even the Samsung is also the part of a design company. Now when it comes to what is their job role, what exactly they are going to do, so these are a couple of things like what exactly they are doing. Like fabrication based company, they are doing the fabrication manufacturing. Basically these are the people, they drive the technology. When it comes to the EDA, so a lot of innovations happen there in terms of the automation, in terms of the tools. So they worked very closely with the fabrication based company. So like TSMC is a fabrication based company. They came up with the 2 nanometer. Now they came up with the 2 nanometers. So how the design company is going to design the chips on that particular 2 nanometer. So they are going to work with the EDA companies, and the EDA companies are going to uh, I would say that develop the tools, and on those particular tools you can do all these designings, and that's where the EDA company play a very important role. Now design companies, if you will talk about the, what is the role of the design companies, they're the market leader in terms of the product. So they create the product and they do a lot of things. So whatever the gadgets and all those things you are seeing in the outside world, that is because of these design companies. But if we think like, okay, we can just only work for the design companies, we don't need to know about the fabrication based companies or EDA based companies, that's not going to work out, because these three are very well interconnected with each other. And as a VLSI engineer, if we think like, okay, I'm in a design company, I know everything, and that's not the right thing, because until and unless you don't know all these three things in detail, then you're not a VLSI engineer. So to be a VLSI engineer, you should know all these things. So next time, whenever you just talk to someone and you just say like, okay, I know a lot of things in a VLSI industry, at least then think twice. Do you know what is the process? What are the things in the design companies? Do you know the EDA companies, what exactly they are doing, how they are developing the tool, and what are their complexity? Do you know about the fabrication based company, how they came up with this innovation thing, and all other things? So I would just say like, okay, just think twice before making that particular comment, like, okay, I know everything, or we have done a lot of things, and I know a lot of things about the VLSI industry. I have seen like, people with a 15-year of experience, they ask a lot of they just made this particular statement like, okay, I'm a expert in the VLSI industry. No, even maybe they are expert in the physical design, they are expert in a design companies related thing, but they don't know anything about how EDA company works. So I think uh, by now you able to understand like, okay, what are the importance of these companies. Next is from the Indian market perspective. I would say there are a lot of other companies also. Like, okay, there are means outside India also. The same model is there, product based and the service based. But especially from the India market, just like I would say, in terms of the numbers, product based companies are less and the service based companies are more. And this there is nothing is like any problem if you're working in a service based company, and why you should go in a product based companies, why you can't work in a services company. So this is the question like a lot of people usually ask. I can understand from salary point of view there can be a difference, but again, salary is something is not going to be a decision maker for your career. It's about like, okay, what exactly you are looking in a VLSI industry. So in a services company, basically they are working for the product based company. They're saying like, okay, I'm the services company, I'm providing these services to the product based companies. And uh, frankly speaking, if you think like, okay, product based companies they can survive without services company, that's not possible. Services company, if you think they are 100% dependent over the product based company, that is also not the 100% true. So it depends like, okay, they are closely integrated with each other. Both the type of the company, both the type of the companies, they need everyone. So that's just a idea about like, okay, what type of companies are there. Now, this is the slide which I was just talking about, the myth and the reality, and the terminology which I just want to introduce here. That is basically the engineers and the engineering labor. So if you will see this particular part, the engineering labor. So this is so as such, all of us think, okay, we are engineer, we are VLSI engineer because we have a degree. We think like, okay, if we have a degree, that is more than enough for anyone just to say, okay, you are the engineer. But frankly speaking, nowadays, engineer, basically there are two type of engineers. One is um, I would say uh, real engineers, and the another one is another category which is the engineer labor. So in any industry, any type of a industry, if I will talk about any type of industry, whether it's a manufacturing industry, there is a very I would say the from the category point of view, you can easily identify. Look, these are the labor class. They are just working. they are machines, and these are the engineers, they are guiding the people, and they are just telling like, okay, do this particular part. So it's very easy to identify there, but in a VLSI industry, on the software industry, it is very difficult to understand like, okay, whether you are doing a job which is equivalent to a engineering, which is equivalent to the labor, or you are doing a real job in terms of the engineer. So I think those who are still in a VLSI industry, they should think twice what type of work they are doing. And if they are working toward the labor side, if their work is toward the labor side, they have to think like, okay, how they should skill themselves and shift it from engineering labor to the engineers. Now that doesn't mean if everyone can shift from the engineering labor side to the engineering side. We definitely, as an industry, we need a balance, and this is just a percentage like, okay, we need more engineer labors compared to the engineers, because of this, because there are a lot of tasks, there are a lot of jobs which is just say monotonous. You have to just run the scripts and it's going to do everything. So that's come under the category of the engineering labor. But once you will start debugging and you just contributing, then you can say like, okay, now I'm just doing some engineering work. Now the question come like, okay, how you can shift it, and whether we should shift it in the in a company or not. So in the entry point of view, whenever you're entering into the industry, till the first 5 year, you can, if you're working as an engineering labor, that's good, that's not a problem. But if you're not shifting your profile from engineering labor to the engineering, if you are not upskilling yourself, if you are not doing the things in such a way that you just shift from engineering level to engineer, then definitely after a couple of years you will figure out like, okay, what exactly I'm doing. So if you want to be a part of that labor thing, then it's good. If you are satisfied, that's good. But if you are saying like, okay, I'm an engineer, then I would say like, okay, please learn, please be expert, please show like, okay, you are capable to do it. And this shift is a something should be a self driven. No one can help you to shift from labor to the engineer part, I would say. That's just something you have to do extra effort. The slide, the last picture which Shivu mentioned, I think that's should be the perfect one. And that if you will just follow that particular part, it will help you a lot, okay, how to move from the labor to the engineer. So that's always try to understand like, okay, what is a myth. The myth is all of us are engineer, but the reality is there are two categories. Now let's talk about the fascinating data. So this is one of the interesting data. I'm sure like, okay, all of you just wanted to understand the salary part. This is a something most of the time, I would say around 70% of people nowadays, students, I would say, the candidates, I would say, they are fascinated because of the salary, and that's the reason they wanted to come into the VLSI industry. That's a fascinating thing, like, okay, they see in this way. So what happened, like, whenever anyone asks me like, okay, they want to switch their profile, they want to enter into the VLSI field, I always ask one question: why VLSI industry? And if they answer like, okay, it's a core field, I have an interest in that particular field, and uh, I think then they're just trying to manipulate the things. They're just trying to show me like, okay, I want to switch into the VLSI field because of XYZ reasons. I'm not able to come up in the starting, I'm not able to join those things, but now I can do everything. But that's not the thing I know. It's because some Sharma ji ka ladka, so it's basically the someone else son or the daughter, they are getting a 25 lakh per annum, maybe in a with the experience of a 4 lakh, and you are working in a, some software company or in the, somewhere in the hardware on the embedded side, you're getting 25,000 per month. So there's a big difference: 25,000 per month versus a 25 lakh uh, per year. And you will say like, okay, that guy was also very similar to me from the same college, and he's getting this much of amount. Why I can't do that particular part? Somehow you realize that particular thing, and then you start thinking like, okay, why can't I just jump from my domain to the VLSI domain? And that's the fascinating thing. And always remember, whenever you are fascinated to because of a money, it's very difficult to achieve that thing, because always you will think about from the money perspective. So this graph, this steps which I have just shown you, like the company 1, 2, 3, 4, there are different categories of the company. If you will see the first to the 5 year, there are the different things. In some companies it's a zero. That means they are not going to pay you in the first year. Second year they will pay you the 4, 6, 9 and 12. And the company 2, they maybe they will have something like 2, 5, 8, 12, 15. This is the step. And there may be some companies, they even the starting salary itself is a 8, 12, 15. And then this is the graph someone just shared on a maybe in the Quora, the Twitter, and you just following that particular part. Just few days back, one of the student, he called me and he was just telling me like, okay sir, I'm spending a almost like uh, so many time in a Quora, and I'm now fascinated about the VLSI industry. Come on, guys. So you're just searching for the VLSI industry. That's the reason you're getting it, this data for the VLSI industry. Even in the software, in the embedded also, you will get the same type of data. It's just a matter of time. It's just about uh, your vision. So in a embedded also, why can't you focus on? Why can't you dream about the Intel? So Intel is not only a VLSI company. It's software also. It's embedded also. It's a IoT based everything. Intel, Qualcomm, even the Apple, Facebook, everyone has VLSI division, everyone has an embedded division, everyone has software division. But I have seen like a lot of software guys, they wanted to shift into VLSI because of the money, not because they want to enter into the core field. They think it's easy for them just to enter into the VLSI industry, and then their future is secure. But that's not true. If if you are thinking about a particular brand, you in any particular profile, you can just go in that particular brand. That's the one thing. Second thing is, a lot of people, they think like, okay, I will start with the company one, and the second year from the 4 LPA package. If I have a 4 LPA package, what I will do after the second year, I will just jump to the 8, or maybe I can jump to the 12. So in the next year, I will jump from 8 4 to 12, or maybe from 4 to 15. Why can't I just jump like that? Maybe some of his or her senior, they did it and they succeeded it, but it doesn't mean like, okay, everyone can do that particular thing. So you don't know the journey of a particular individual, but on the basis of the success story, we always think like, okay, we will also follow the same path, but that's not possible. So always what you have to do, you have to think uh, uh, twice before making all these decisions. And that is the place where you need awareness, and that is the place where you need a mentor, and you should just ask that particular part to them. This is the brand. This is again a fascinating data. I think all of you know, like, arm cadence. So I just capture the 3 6 big, I would say the company name, but there are almost like uh, 10 15 such brands are there. People are fascinated. Now, this is a reality. Reality in the sense, like, I just divided the services in MNC. We think like, okay, in MNC, as a fresher from the tier 3 college, we can just enter with a package of 8 lakh. No, that's not possible. Initially, they will give you the 20, 40 thousand per month. That is basically as an intern. And then on the basis of your performance, they will convert into the full time. Entry is not that easy. People think like, okay, I'm capable, I can do it. My friend can do it. Why can't I do it? So they can't understand like, okay, if someone is paying you money, then definitely they will grill you also. They will just check you whether you're capable or not. uh, I know couple of companies, they for them skill set is important, but for them the attitude is also important. And the student don't understand that particular part. Attitude is also important. And during the interview process, you will never come to know like, okay, they already they are going to check uh, uh, your attitude. by even by your resume itself. The first look of your resume can give me an idea like, okay, what is your attitude, whether you're serious about your profile, whether you're serious about your presentation, whether you're serious about your skills. So don't think like, okay, if my resume is not good, doesn't matter, I have a lot of skills. Similarly, in a services company, the reality is there are companies, they are going to pay you 0 rupees for the first year, and on the top of that there is a commitment of 3 to 5 years. We always miss this particular part. But yes, if you're ready to give your commitment for the next 5 years, then is good, because they are giving an opportunity. So but it doesn't mean like, okay, if they are not giving in a if you are not ready to commit to a company for the 3 to 5 year, because what does it mean? That means you're behind money. That's a very simple thing. And if you're behind money, there may be rate of success is very less. So that's very important. So if someone is giving an opportunity to enter the VLSI industry, if you're giving it 3 to 5 year of commitment, doesn't matter, just work hard and just prove yourself, and then the money will come, like I said. So that's a reality. Like, okay, the people don't understand this particular part. Now, few people usually ask me like, okay, he's getting a 24 LPA package, and from the campus, for the tier one also. So I just give an idea like, okay, that how the salary things are divided, and the 24 LPA. The similarly, it can be a 30 LPA also. So I've worked with a lot of companies, managers, and I know like a lot of IT, IITians also. So if let us suppose a company will come with a 24 LPA starting salary. So this is going to be the salary structure, like 3 lakh as a joining bonus, which is the first year. That's all. 9 lakh of shares, which is going to invest in the 3 years. If you just leave in between, you will lose it. Same with the joining bonus also. It says 3 year of commitment. If you will just switch the company, if you just leave the company, you have to pay that particular part. 2 lakh of variable pay. That means if you will perform good, then they will give you that particular uh, amount. As such, the bottom line is the 10 LPA, the turn like is something which you will get as a part of your salary. But we don't see these things like, okay, 3 year commitment in the joining bonus, 3 years the investing time, and there is a variable pay. Like, okay, if I'm not going to perform, I will not get that particular money. We just see that number 24 LPA. But the same thing, if you will go with some other company and off campus, or maybe some small company, and if they are saying, okay, I will give you the 10 LPA or the 8 LPA, you will say like, okay, oh no. So 10 LPA, 8 LPA versus 24 LPA is a two difference. But here also indirectly you're giving it 3 to 4 year of commitment. I think that's very important. Now these are the last two slides. Undisclosed fact. A lot of people, they usually ask. So in the interest of time, I'm just running too fast, but yes. So these two slides, one is how the screening happen. It's basically on the base of the marks, and how the entry is there. So in a services company, so all these things are like, what are your chances to enter into the VLSI industry if your marks are less than 65%. So yeah, so this is the it should be the less than 65%. Yes. So it's if it is a less than 65%, then how many chances you have? The 5% chances I'm just saying, and this is again I'm just saying on a uh, higher side. So when I'm saying the 5% chances, that means in your college itself you should focus this particular part. And nowadays, getting a 65% marks is, I will say like, okay, it's very easy. So if you are not getting a 65% marks, the industry people, they think like you have some problem, and that's the reason they came up with this particular benchmark. No one is going to tell you, no one is going to display this particular part like, okay, the 65% we are not going to uh, uh, hire you, but this is a something which you should know very well. Second thing is, if it is between 65 to 70 in MNCs, in the big companies, again, they have a thought process. Like, okay, the people having a less than 70%, they don't have that much of skills. That's the one thing. Second thing is, everyone is applying for a position in those companies. Now they have to screen. How they are going to screen? They are going to screen based on the marks, because they don't have any other thing. On the basis of that, they will just screen out. And Obviously, if you have a candidate with the 80% or the 90% marks versus a candidate having 60%, 65% marks, if both are equal, then nothing is going to, obviously I'm going to I will just go with the 80% marks, even if I have to hire the one person out of those two. I cannot give the chances to the person having a 65%. That's the reality, so you have to accept that particular part. Yes, services companies definitely they can do it, but definitely if they will do it, they need a commitment from you. But if you don't want to give a commitment, and if you have a less marks also, come on guys, so it's a business, so no one is going to entertain you. The next is greater than 70%. Yes, as such 100%, if you have, then you will get it. This is basically the in case of a employee, if you will see in the MNCs, 80%, maybe more than 70%, 15% as a part of between 70 65, there is a 5%. And a service is going to be, the distribution is going to be like 50-50. That's the average one. The last one is basically on the basis of the passing year. Specifically, intentionally, I just put this particular slide here because a lot of people usually ask this particular question. I'm a person pass out in 2015. Can I get a job in VLSI industry? So my question, the very first question, why you want to shift your career after 5 years? What exactly you have done in the last 5 years? And then the way they explain me, like, okay, first 2 year I was just doing this thing, then the next 3 year I'm just doing this thing. So they have a, obviously I've interacted daily almost like the 10 people of different groups and everywhere. So it's very so I know very well, like, okay, whether they are the right person or they are just making sense or not. But yes, this is the fact. If you are the 5 year earlier, you have passed out in 2015 2014, I would say, please guys, please, until and unless you have a very strong reason, don't try to change your profile, don't try to jump in a VLSI industry. VLSI industry is not going to entertain you in that particular perspective. Yes, there are chances, there are cases, I'm not going to deny it, but those are the exceptional one. So if you are 2015 2014 pass out, please, that's my recommendation. There are people with a 3 year earlier, they just pass out like 2018 2017 pass out. Yes, so you have good chances. But again, why you just wanted to only MNCs? Why can't you just go the route of a services company? They will give you the chance also, because if you can just prove them, like, okay, you have 70%, you are 3 year a 3 year earlier, you just pass out, but you have to just show them, like, okay, you are a mature candidate, because in an industry your attitude also matter. So if you have a good attitude within this particular time frame, you can get it definitely. So I'm not compromising with the skills you should have, but yes, you should have a good attitude. So in the 3 year we usually assume, like, okay, you're mature enough, and then the services company can entertain you, like, okay, at least you're the mature person. Even our industry, the MNCs, they are also hiring, they are also hiring some percentage of their employee, which and so there are different policies, they are hiring from that particular pool also. But if you're thinking, like, okay, you will get an entry, easy entry, that's not possible. So easy entry anyways in a VLSI is not possible, so you have to just understand that particular part. Now if a 2 year earlier, again, uh, it's the most welcome in the services industry most of the time. In MNCs, depending upon which type of companies I'm just talking about, on the basis of that, it's very difficult if you don't have a relevant experience. So that's these are the numbers which you will not find anywhere, and I'm just sharing on my basis, like I on my experience. And I'm just highlighting this thing. Maybe few people don't like this particular part, but I'm okay with that because I know this is the fact. Okay, so that's all, and with that, just I'm done. And I can see there are a lot of questions over the chat window, and if Prerna allow me, maybe what uh, uh, I think we have some time, Prerna, am I right? Maybe I can just unmute you. Okay, yes, we have some time. Okay, so let me just go back one by one. There are a lot of questions from the top. So I think Okay, so there is a question. Is there any opportunity for the intern 2018 pass out looking for the job opportunity? I think that's something you can just check the website and you will figure out. But like I said, 2018 not a problem because 2020 is just like gone. So don't worry about that particular part. You have to just check the company website and you will figure out like okay whether there are opportunities or not. How one can start career in VLSI after BTech skill sets. You should have. So Alok asked this particular question. So you should have a good skill set, and if you have a good skill set, then you should have a good profile. Start applying. Ask people over the LinkedIn if they can refer you, and then you can start your career. But like I said, I just gave you the data like okay what should be the what should be the criteria. If it is 70 plus, chances are more. 70 minus, when I'm seeing the percentage wise, chances are little bit less. And then again depending upon how earlier you have passed out. Similarly, someone asked like okay can a student attend the conference such as TV contact. So guys, you can attend that particular part, not a problem. Always there is a fees, you have to just pay that particular fees. In the last so many years, I'm not able to afford that particular fees. It's in a dollar. So but you can do it if you can afford that particular thing. But it's not only the DAC or any uh, uh, design conference and all. Is basically always like you have to just see like okay what do you want to get from that particular conference. So you should know like okay what should be the output or what exactly you want to extract from a particular conference. So if you know that particular part, if you are clear with that particular thing, I can say like okay you can interact with anyone, any mentor, any industry people, you can extract that particular part, even for the blogs also, from the article also. But nowadays, like you can see a lot of information is present over the internet. I will say like okay if you want to search it, you can do it if you cannot afford that particular thing. Okay, then there is another same question, which is better joining an MTech will SI industry or some industry based training. So the question is good. And sir already Preeti Ranjan sir already answered this thing, but I will just say one thing. Tier 3 college BTech, Tier 3 college MTech, it's the same thing. Tier 3 college BTech, go with the Tier 1 college MTech, then it's going to make a difference. So you should know what exactly you wanted to get from the MTech. If you are looking for a job, then if you are in the same education system, like where you will not get the education, not the learning, whether you will do the PhD also, it doesn't matter. So you have to think twice like okay what exactly you're getting after doing a MTech. So there are a lot of colleges, it's the same thing, BTech, MTech. Even if you will do the PhD, it doesn't matter. So don't go with the MTech there. When it comes to the research point of view, if you want to do something, if you want to learn something, then definitely you should go with the MTech, no question, irrespective of whether you will get a job or not. So it's all about doing a MTech for the VLSI job. And if you're talking about a degree, ah, don't go with that. Spending a 2 year of time and then the so much of money, just spend that much of time, and in the services company you will get more than that. So just one advice, like spending let us suppose 5 lakh 6 lakh in a MTech and spending 2 year also. And why can't you just go in a services company, spend 2 year there, and just get some money also. So there you have to spend like 3 years or 4 years. So from the financial point of view also, everything is going to be the good thing. So just think before you decide for the MTech. But if you are interested really in the research, if you're really interested to learn something, then you should go with the MTech. When it comes to the layout design engineer, so memories. So that's the future of the VLSI industry. I think if you will just try with the memories, then you will get it's a good future in the layout side also. Xyling and the related to which process. Okay, so now little they're asking about like okay in terms of xyling thing. So it's the FPGA part. Somehow I don't connect these two things, FPGA and VLSI. One is a full custom, one is a other thing. But yes, I think that you can just check it in their website, like okay, what exactly they are doing right now. I don't have that much of idea. There is a another question: what are the terms of physical, formal, functional timing and verification? I think this is too technical, and maybe we can just take it offline. Next is what? How should one proceed and gain knowledge about VLSI in a better way? Reading articles, listening. I would say the all the YouTube's resources, books, and just part of a discussion. That's a good thing. Just you should have the this thing like okay, you wanted to learn something. Fabrication based domain, Sandeep, don't go there because that's a completely like in a labor job. So if you are thinking like okay, you are going to fabricate the thing, so if you are doing a technology related thing, yes, then again it's the same process like you're entering into the VLSI field. But if you are saying fabricating the thing, you want to fabricate the chip, that's the mechanical or the chemical engineer, not the engineer also. So they are doing this particular part. When it comes to future of physical design engineer, yes, physical design engineer is a stage, that is a stage of basically the whole process. So if the VLSI is there, definitely physical design engineer going to be there. Next question is asked by Ajay. Is like any, is there any chance India will get its own foundry? Yeah, so from the last so many years, like okay, people are saying, but we already have one foundry, SCL Chandigarh, just a 180 nanometer. We are doing that particular part. But if you are thinking about the TSMC and all, I don't know. So it depends on the several factors. What are the codes and the roles of the foundry companies? What exactly the type of fields, the work they came under the engineer labor? I think we can discuss this thing later on. We can compile these questions and we can do that particular thing. Easy entry. Okay, there is no easy entry, Alok. There is no easy entry. There is nothing easy. Easy word is something is a subjective again. So maybe for me it's very easy to speak in this like in front of 100 people, but maybe it's not easy for you. So it's a subjective. But as such in a industry, as such in VLSI, there is no easy entry. Then there are a lot of questions, I think, but in interest of time, I would say okay, maybe we can just take it later on. And so we will note down all these questions, and after that, maybe what we are going to, we will just compile those questions, and then we can publish it on our website, or maybe we can have a some session later on where we can address only your queries or questions. So Prerna, now it's over to you.
Right. Thank you,
Okay.
Puneet. And your session was very thought-provoking and very, very informative. So that brings us to the end of our session. Again, we want to thank you all for being a part of our first session of Expert Talk. I am sure you must have found these talks informative and useful. Um, just so you know, guys, our next Expert Talk session will be on the third Saturday of next month, which is 15th of August. Since it's the Independence Day, our session will commence in the second half of the day, and we will share the details as we will proceed. So in the end, I just want to sum up this session with a quote that resonates with the theme of our Expert Talk. For there will be no darkness of ignorance, and only wisdom as a shower of teachings will be bestowed upon us. Thank you guys again. Take care and see you next time.
Thank you, everyone. So thank you, Preeti, Ranjan sir. Thanks a lot. And I know like there are a lot of people I'm not able to just talk to them, but I really thank everyone. Like okay, you made this event as a wonderful event. I can see like there are almost like 120 candidates in between, and there are I think in a YouTube channel there are a lot of people are watching, so you will get all the recordings and everything. And
Thank
let's
you,
just
Puneet.
connect.
Thank you, Prerna. It was a pleasure interacting.
Thank you, thank you, thank you.
Thank you. Welcome, sir. Thank you,
Sir.
Dr. Panda.
Okay, thanks a lot, everyone. Bye bye.